Hey everyone, Grayson here. I'm actually a little bit under the weather, so forgive me if I need to blow my nose or cough or something. I'll mute myself. But I'm doing well other than that. Uh, Looking forward to tonight's debate. It's a little bit of a strange topic here because I don't think either of us is necessarily going to be building an affirmative case. TRock is going to be bringing 5 lines of evidence that he thinks show that the Earth cannot be billions of years old, and I'm going to be trying my best to debunk them using evidence and science. So generally, I am an enthusiast for science. I love most topics in science, from quantum physics to geology to evolution. And yeah, I just started my channel towards the beginning of this year, Based Theory. If you search on YouTube for Based Theory, it should come up. I do debates on all of these topics, as well as live stream after shows and random videos about just random subjects in history and science. So if you like any of that stuff, definitely check it out.
Grayson, appreciate that intro. I do have your channel linked in the description box. So to the audience, if you like what you're seeing from Grayson, definitely check out his channel. He does put on after shows to a lot of the creation evolution debates that we host. And so I always appreciate that as the debate continues into the night. TRock, you don't have a channel, but I do have a couple of your past debates with us linked in the description box for people to check out. So TRock, great to have you back. How you been, and a little bit about yourself.
Thank you, Donnie. I appreciate this opportunity. Thank you to the audience for tuning in. Per Grayson's comments, we're going to go through 5 specific subjects on determining evidence for a young Earth. And we're going to start with, I'm going to say what they all are real quick. We're going to start with Earth's magnetic field. And the other 4 in order will be erosion rates, lunar recession, carbon-14, and then dinosaur soft tissue. So some of them we might not spend a whole lot of time on. Some of them we might be a little more in depth with. This happens to be one of Grayson's favored topics. So we're going to start there, and that's fine. Anyway, enough about me. I'm ready when you guys are.
TRock, Grayson, thank you both for those introductions. You're both no stranger to this channel anyways, and so I'm looking forward to this. You're both excellent debaters. You're both well knowledgeable on this topic, so this will definitely be a debate to remember. 5 specific subjects on determining evidence for a young Earth, and so in a way, this is young Earth creation on trial, and Grayson is going to be critiquing those 5 specific subjects. I know he's excited. I'm excited. We're all excited. So let's get right into it. TRock, I know your first point, you are going to take about 10 minutes. And so let's get started.
In the 1970s, the creationist physicist, Professor Dr. Thomas Barnes, noted that measurements since 1835 have shown that the field is decaying at 5% per century. Also, archaeological measurements show that the field was 40% stronger in AD 1000 than it is today. Okay, Barnes, the author of a well-regarded electromagnetism textbook, proposed that the Earth's magnetic field was caused by a decaying electric current in the Earth's metallic core. The physicist Dr. Russell Humphreys believed that Dr. Barnes had the right idea, and he also accepted that the reversals were real. I'm going to segue for just a second. There are some creationists in the past that have denied reversals. I can take them or leave them, but the appearance to me is that they are quite real. I don't need them for the sake of arguing a young Earth, I'll put it that way. But nonetheless, they do appear to be quite real. So he modified Barnes' model, Dr. Humphreys modified Barnes' model to account for special effects of a liquid conductor like the molten metal of the Earth's outer core. If the liquid flowed upwards due to convection, hot fluid rises, cold fluid sinks. This could sometimes make the field reverse quickly. Now, as discussed in Creation Volume 19, Dr. John Baumgartner proposes that the plunging of tectonic plates was a cause of the Genesis flood. Dr. Humphreys says these plates would have sharply cooled the outer parts of the core, driving the convection. This means that most of the reversals occurred in the flood year every week or two. So that's pretty rapid for reversals. Okay. After the flood, there would be large fluctuations due to residual motion, but the reversals and fluctuations could not halt the overall decay pattern. Rather, the total field energy would decay even faster. This model also explains why the sun reverses its magnetic field every 11 years. The sun is a gigantic ball of hot, energetically moving, electrically conducting gas. Contrary to the dynamo model, the overall field energy of the sun is decreasing. Dr. Humphreys also proposed a test for his model. Magnetic reversals should be found in rocks known to have cooled in days or weeks. For example, in a thin lava flow, the outside would cool first and Earth's magnetic field in one direction and record Earth's magnetic field in one direction. The inside would cool later and record the field in another direction. So this was a particular prediction by Dr. Russell Humphreys. 3 years after this prediction, leading researchers Robert Coe and Michael Prevost found a thin lava layer that must have cooled within 15 days and had 90 degrees of reversal recorded continuously in it. And it was no fluke. 8 years later, they reported an even faster reversal. Currents in resistance inductance circuits always decay exponentially, not linearly, after the power source is switched off. For example, in a simple electric circuit with time t with initial current I, the resistance R, and inductance L, the current is given by the equation little I equals big I times E raised to the quantity of minus small t divided by tau, where tau is the time constant, L divided by R, the time for the current to decay to 1 over E, or about 37% of its initial value. The non-dipole intensities fall off with increasing distance from the Earth's center much faster than the dipole intensities. So the non-dipole parts are not able to contribute nearly as much energy to the total as the dipole part. So let's see what else I got here. Okay, so Coe and Prevost carefully sampled a relatively thin 1.9 meter lava flow. That's approximately 6 foot. Designated as flow number B51 at a point where their team's previous investigations had suggested a rapid transition, magnetic polarity change, was likely to have been recorded. This period of 15 days is undoubtedly an overestimate. Let me back up a second. This is a direct quote from those two scientists, and this is a secular source, and they are deep time advocates, not creationists. So he says this period of 15 days is undoubtedly an overestimate. Nonetheless, even this conservative figure of 15 days corresponds to an astonishingly rapid rate of variation of the geomagnetic field direction of 3 degrees per day. With due caution, Coe and Prevost thus felt prompted to search for alternative explanations. However, since other hypothesis requires special pleading, they decided that the most straightforward interpretation explains the data best. That is, the balance of evidence now in hand weighs, and again, this is a direct quote out of their paper. The balance of evidence now in hand weighs in favor of rapid geomagnetic field variation. We think that the most probable explanation of the anomalous remnants directions of flow B51 is the occurrence of a large and extremely rapid change in the geomagnetic field during cooling of the flow, and that this change most likely originated in the Earth's core. This interpretation must remain tentative until our investigation is completely finished, but if true, it has important implications for the reversal process and the state of the Earth's interior. So I'm going to stop there and let Grayson take his time to offer his insight.
Yeah, okay. That was so, I mean, I feel like I need you to maybe clarify a few things, because I feel like you were kind of offering maybe some specific evidences and context, but I feel like the overall point might have been missed. Like, what is your reason for assuming that the decay rate of Earth's magnetic field strength is constant?
I did not say it was constant.
You said it was 5% per century.
That's not a constant rate, technically.
That's a
That is
constant rate of 5% per century.
okay, but when you and this is where not sharing my screen is a big disadvantage. But when you actually do the math, you can see numerically that it's not 100%, 95%, 80 or 90%, 85%, so on and so forth. That's not what 5% per century means mathematically. It's not. It doesn't translate to a quote unquote constant. So the
5%
real
per century is a constant rate of 5% per century. It's not a linear rate, but it is a constant rate.
Okay, fair enough. If you define constant, like that's fair enough. We don't have to really go back and forth about that point. So
But
the other way,
my question
the other
is,
way,
why are you
okay,
assuming that?
the other way specifically to define that is a half-life of 1,400 years approximately. It's probably a little over that.
So why do you think that the Earth's magnetic field decay has a half-life? Why
So,
would that be the case?
Because in electrical circuits, there is a standard equation for describing either, and it actually applies to a number of electrical parameters, but voltage drop, for instance, in a battery uses this same formula. Collapsing magnetic field uses it, and I believe other things like capacitance and probably some other electrical parameters also use it. In other words, the formula is very standard science.
Why would that formula apply to the Earth's magnetic field?
Because it's electromagnetism, and that's how the theory was developed to arrive at this equation. I read off the equation earlier, and I'll do it one more time. It actually looks.
I heard you the first time that you read off the equation. I just don't think that any geophysicist applies that equation in this case, and I'm curious about why you think that it is an appropriate equation to use in this case.
Because that's how all electrical currents are described.
Yeah, but that is not the case here, because like the actual thing that is powering the Earth's magnetic field is the cooling of the core. So energy is continuously given to the system, right? The convection of the outer core is what causes the magnetic field. It's constantly generated. So energy is continuously supplied to it. So it doesn't make any sense for it to have a half-life.
Actually, what you said is not technically true. Does cooling play a role? Yes, but electromagnetic fields are generated by mechanical motion. So you need.
And what causes that mechanical motion?
You need the convection. You need the convection currents.
Yes.
Well,
which are powered by the cooling of the core. Yes.
Let's back up just a hair. That's actually not the only thing you need.
When you said that the hot fluid rises and the cool fluid falls, that's correct. It falls onto the inner core where it is reheated by the core. Thus, the inner core cools to heat the outer core to continually power the convection currents. And the convection currents are made of a fluid of molten iron and nickel, which conducts electricity. Thus, you have a movement of electric charges, which definitionally, by the laws of electromagnetism, will generate a magnetic field. This has been known since the 1800s.
So I think we agree on the point that you have to have the mechanical motion. I think we don't agree on you're kind of painting this picture of somewhat of and I don't mean this literally, but you're approaching the idea of this perpetual motion machine, where this cycle just keeps on repeating at more or less of a steady rate. Now, here's how we know that is not the case. There are about 200 years worth of data describing the decline in the field strength. 200 years worth of data. That's better data than we have for a lot of things.
We have a lot more than that.
Yeah,
we have an entire field of paleomagnetism.
Yes. But specifically on real-time measurements, paleomagnetism aside, real-time measurements of the field strength is not the same as what you do when you're looking at the seafloor and trying to decipher what happened in the past. These are two different things. We've got about
here's 1 point I want to just bring up really quickly, is that in any system that has a half-life, right, you never see, you see only a decline, right? You don't ever see an increase. But when you measure Earth's magnetic field strength on small time frames, like in a week, you're going to see ups and downs and ups and downs. it is not the behavior of a system that has a half-life. No system with a half-life does this. Like whenever you have a radiometric decay, if you look very closely, you're not going to see ups. You're not going to say increases in isotopes and decreases in it's only decreases. It's the same with an electric circuit. You're not going to see ups and downs. You're going to see a decrease. So this system does not behave in a way that is modeled by a half-life.
Okay, so let me just say it very straightforward. You are technically completely incorrect on this point. Now, how do you get ups and downs in the Earth's magnetic field? So there are ups and downs. There are spikes recorded. If you take a look at a graph of it, you'll see these rather large anomalous spikes that you're referring to. That is true. Part of what you're seeing, though, is a spikes. So there is a what's called a dipole moment and non-dipole moments in the Earth's magnetic field. And so the dipole moment is how you think of a normal magnet, north and south. And then the non-dipole moments, they're also referred to as multipole because they're more than two. They could have, for example, 4 norths and 4 souths kind of thing, and arranged in different angular configurations. But the spikes that you see are not in the energy of the field. They are in the field strength in terms of, and I'm not sure whether they use Gauss or some other unit of measure for this, but anyway, it's referred to as field intensity, for example. But field intensity and field energy are 2 different things. So you can get spikes, and to put a finer point on it, the reason we know you're not historically correct either is because besides just having these, like I said, semi-perpetual motion convection currents going up and down in the core, you also have literal physical mechanical motion to consider, i.e. tectonic plate movement. So I think everybody knows there is a tectonic plate that looks like it has dived almost to a 90-degree angle down towards the core. That type of tectonic motion can drive the convection currents, which is what my presentation was actually describing, can drive those currents and flip the field. And in doing so, it can also spike the field intensity. But as my presentation showed, let me read this one more time, real short, if I can find it real quick. Give me just a second. But essentially what happens is reversing the field accelerates the decline of the field energy. It cannot maintain it perpetually. That's completely impossible. It's not even rational physics. All it does is boost the field strength for a little while, but the net energy is actually accelerated in its decay.
Yeah, I mean, I never brought up any kind of field reversals. I was only talking, or like the total energy. I've only been referring this entire time to the field strength and why the field strength cannot be modeled by a half-life decay pattern. So these spikes totally rule out the modeling of that pattern. But overall, I would just say there's no reason to believe that the decline in field strength has been constant or has been exponential or follows a half-life. There's no reason at all to believe that that is the case. We have plenty of reason to believe otherwise. The entire field of paleomagnetism completely demolishes this point. Like whenever we see like rocks that contain magnetic properties, whenever we see them harden, right, the magnetic aspects of them will align with Earth's magnetic field. And the percentage of how much it aligns can show us data about the field strength. So we can see whenever these magnetic rocks are formed, we can see what the field strength was when they were formed. And we have a whole lot of data about this that we show that the field was both stronger and weaker at various points in the past. It's not like the graph is a straight line down or an exponential half-life curve. It is literally just a very chaotic pattern of ups and downs throughout the Earth's entire history. That's what the data shows. And one last thing, beyond the paleomagnetic data, we have other independent sources of data that validate this. For example, we can look at like beryllium isotopes that are formed in the atmosphere. And if you have a stronger magnetic field, more cosmic rays are going to be deflected and less beryllium isotopes are going to form in the atmosphere. And when we look at marine sediments and we look at the history of beryllium isotopes as you go down the layers, they match onto the paleomagnetic data very precisely. These are two completely independent methods that corroborate each other and show us that Earth's field strength goes up and down in the past. And, you know, I mean, I emailed several experts in preparation for this, for these different points, and a geophysicist said that no one in the field would ever claim to be able to predict what Earth's magnetic field strength is going to look like in the future. It is a complex, chaotic system determined by the mechanics of how these convection fluids are moving in the outer core. And we don't have any good models to predict how it will be in the future, right? It's a complex, chaotic system. It's not predictable. No expert in the field will claim to be able to predict it like a half-life model, which would be highly predictable. Nobody is claiming this.
Are you done? So again, you're technically completely incorrect. And having said that, I would not disagree with your geophysicist friend at all, because you're not describing what we're actually plotting on a graph. If you're plotting the energy of the field, it's an exponential decay per standard electromagnetic physics. It's a very standard deal, but we're not projecting or predicting a perfect half-life decay curve like what you would associate with just doing basic model math. That is not what we're describing. That is not even what the graph looks like. Your idea of spikes, again, you've got to delineate between field intensity and the energy that drives the field. Less energy in the field equates to less net energy or less net intensity in the field. They're completely bound to each other in that regard, but it's the energy that drives it. It's the amount of energy that tells you what that's supposed to be. So again, I would completely agree with your geophysicist friend that you can't make any predictions in it. But again, go back to what I was saying about plate tectonics. In inducing electromagnetic fields, period, you need mechanical motion. Am I still coming in okay? And plate tectonics provides that motion. So what you would normally expect is on a calm millennium where there is no tectonic motion happening, you would expect a much smoother curve like what you were trying to describe.
Hold on a second. Hold on. Plate tectonics occurs on the lithosphere, on the top of the mantle. We're
Yes.
talking about the movements that we're talking about are in the outer core. There's like hundreds of kilometers of difference between those two areas. They're like the plate tectonics is not really affecting the magnetic field very much.
Today it's not, but it did in the past. And I don't think anybody disagrees that there is literally a plate that has taken a dive into the mantle.
We're not talking about
that
the mantle.
Dive,
we're talking about the core.
And I'm telling you, it's deep and it goes all the way close to the core. The only part the solid core does for you is provide a thermal battery for you. That's all it really does.
Hold on. Outer core, different than inner core. Inner core is solid. Outer core is liquid, even though they have the same chemical composition.
Say that again.
The outer core is fluid. The inner core is solid. They're both the core. They're both iron and nickel, but they're not the mantle.
Okay.
So the movement that generates Earth's magnetic field comes from the outer core and is powered by the cooling down of the inner core.
That's not even relevant. You've got a
that is how the Earth's magnetic field is continuously.
You've got a plate that has dived so deep, so whether you call it the mantle or the outer core, the liquid portion of the outer core,
it's not going to the outer core.
It has gone so deep that it is basically thrust thermal currents down and created a cooling effect. So two things have happened simultaneously. One of them is the thermal currents you were describing earlier, and the other one is literal mechanical motion. And
yes,
so
there are a number of things that can affect the convection currents. I mean, like literally a solar flare from the sun can change the actual movement of the convection currents because of this thing called magnetic induction, which is how all this works. A moving electric charge generates a magnetic field. If you change that magnetic field or impact it, like with a solar flare, that's going to change the movement of the electric current flows in the core. So it's a feedback loop. It's a complex, chaotic system. It is not modeled by any kind of half-life behavior. It is not modeled by, it literally stresses the most complicated computer simulations we have at the moment to try to model these complex partial differential equations. It's a very complex, chaotic system.
So going back to your idea that it's not modeled by half-life equations, if you take that 5% per year that you called a constant, and I will agree the rate itself is a constant rate, but the effect over time is an exponential curve, because you can do it either way mathematically. You can take the 1400-year half-life and you can plot over time what the field strength should be, or you can take the 5% idea and just do, and I've done these both on an Excel spreadsheet. Hopefully I'll get to share my screen again before the night's over here, but I've already done this on the screen to show you. Mathematically, they're the same. 5% per year, or call it 1400-year half-life. Mathematically, they are identical. They come up with the exact same values in the exact same places.
Because you calculated the 1400-year half-life using a 5% per century number. That's how it was calculated.
No, you can calculate, you can do the math completely independent of each other. You don't need 5% per year to deduce the other, because you can also just use the standard physics equations for electromagnetic decay.
Yeah, I don't think so. But I also, largely beyond that, I don't see any reason to do any of these equations when they directly conflict with the evidence that we have available.
The evidence that we have available.
How would we have the paleomagnetic evidence that clearly shows that the field was both stronger and weaker in the past?
So yeah, let's talk about that evidence for a minute. Can you go ahead and take your time and describe that for just a minute?
I already did. Yeah.
So I'll be honest with you. I'm a very detailed kind of guy. I don't think you gave any real detail behind the idea that paleomagnetic currents tell us anything.
Well, I didn't say paleomagnetic currents, did I? I said the actual rocks that contain magnetic properties, like ferrous rocks with iron in them, right?
That's paleomagnetism.
Yes, that's paleomagnetism. Exactly. That's what you're asking about, is it not? So when you examine these rocks, you can tell what strength of a magnetic field was affecting that rock at the time when it was formed. And I'm not making any assumptions about billions of years or whenever these rocks were formed. Nothing. Okay? All I'm saying is that when these rocks formed, whenever they formed, you can tell how strong the magnetic field that was affecting them at the time of their formation was. Because you're either going to have a very large number of these iron atoms that are going to have their magnetic moments aligned with the field, or you're going to have a relatively small fraction of them aligned. And depending on the fraction, that's how strong the magnetic field was during the formation of the layer. So we can just look at the ferrous rocks that we have in the world, and we can look at what the field strength was when they were formed, and we can see there's a huge variation. There's some that are higher than today. There are some that are lower than today. The magnetic field is literally all over the place in terms of field strength.
So, ironically, the way you described it, I don't disagree with, but you're not really understanding what it is you're seeing or why it is you're seeing it. Yes, you can absolutely see spikes in the field intensity, which you're calling field strength. Field strength can highly vary based on the field energy. So you can see spikes in the strength all over the world. That's not being contested at all, but that's not, you're not putting two and two together of how that comes about. That comes about through a rapid reversal is actually what is driving that. You need the reversals to cause that to happen. If there is no reversal, if this is more like the semi-perpetual motion machine you described with these convection currents just cycling through at a very steady rate, you would not have the spikes that you're describing. They would be very steady.
No, you would still have the spikes.
No, you have to have the reversals.
Like I've been saying multiple times, this is not some kind of perpetual motion steady state machine, right? This is a complex chaotic system that has multiple inputs and a feedback loops. Okay, this is like it can get totally really crazy to calculate. If it was as simple as TRock was saying, we would be able to model this with computer simulations. But even our most advanced computers right now cannot model this behavior. Like it's a very crude modeling because it's so complicated. The partial differential equations involved are too much for even most supercomputers. So don't buy what he's saying about this is a super simple situation. It should be a super steady state. There's no spikes and troughs. Absolutely not true.
I did not. You're completely misrepresenting what I said. Completely misrepresenting, and I don't think you at all understand the technical implications. So you talked about solar flare, for example, being able to affect the field strength, I guess is what you were saying.
Yeah,
I wouldn't even bother contesting that, but I would say that it would be super insignificant, and the variation you actually see in the spikes in the field strength that you've described cannot be accounted for based on that type of input.
Yeah, well, you say that, but the feedback between the magnetic field and the moving electrical currents in the core is what is so complicated. These feedbacks are so complex that you're just writing them off and saying they're insignificant when literally our most advanced supercomputers cannot model this behavior.
I'm not disagreeing with that. That's
okay. So you're
significant. You're missing the point that you're misrepresenting what I'm saying, and you obviously don't understand the technical implications.
Pause for 1 second here. Do you agree that Earth's magnetic field is generated by the movement of electrical currents in the core?
Technically, no.
Well, then what is it caused by?
So, backing up all the way to the origin of the Earth, something had to induce a relatively large field. Something had to induce that. And it had to be through mechanical motion.
Well, it's still being induced today by the same process. It's continuously induced. That is the principle of magnetic induction. So I'll just preempt this right here. If it's not magnetic induction, then there is no physics that could explain it, because Earth's core is at a higher temperature than the Curie temperature, which is the temperature at which a normal ferrous magnet, like a permanent magnet or any kind of magnetic field that's constructed by the alignment of magnetic moments of the atoms that make it up, that doesn't work at such a high temperature. So the only thing at that high temperature that could physically be generating a field like this is the movement of electric charges. Like it's got to be magnetic induction. There's no other physics that can explain it.
So let me clarify a really important point there. When I'm not even disagreeing with some of the technical ideas that you're putting out there, so too complex for a supercomputer. I'm not even contesting that. I'm not describing some sort of simplified version of it. What I'm saying is that over time, and we have 200 years worth of data to show this, plus we've got the data itself, plus the fundamental equations that you use for magnetic decline. But there's probably a really important physics point in here that I don't think you've necessarily keyed into. And that is that whenever you have a collapsing field, the collapse of the field itself induces an increase basically when it induces a voltage. So as that magnetic field is collapsing, it induces a voltage. The voltage in turn re-induces a collapse. So it's a cyclic thing. And that is exactly what the equation that I was trying to describe earlier, that's exactly what it's describing, is the cycle of collapsing, inducing a current, rebuilding the field, but less. And the reason is because whenever you have current passing through like that, you hit resistance, you produce heat. So your energy is lost in the form of heat.
So all of these equations that you've been bringing up this whole time, none of them factor in what if energy is continuously being added to the system. That invalidates all of
I just told you. I just told you.
No. You said that if the energy is constant, then you'll have it decline over time.
I did not say that.
Adding energy to the system, as is happening with the Earth, like as the core cools, that is adding energy into the convection flows. Then none of these equations apply because energy is continuously being added.
You're literally making up things I didn't say.
Okay, well, I'll tell you, for those equations of electromagnetic decay, the assumption in order to be able to use these equations, what makes them applicable is that energy is not continuously being added to the system. It's electric, it's a field, it's a decay in a closed system.
No.
That is how those equations work, yes.
Where is the energy coming from? The energy is literally coming from the collapse. So it collapses and induces a current, which is the energy that drives the spike again. So it's a cycle. It is the same cycle you get in a battery, for example.
So you're not adding any more energy than you had at the start.
Correct.
Yes, but that is not the case in the generation of Earth's magnetic field. That is not the case. You are continuously adding energy.
No, you're not.
Yes, you are. You are changing heat energy
the Earth's
mechanical energy.
Let's use a little bit of common sense here for a second. The Earth's core, the inner core, the outer core, the mantle, the entire thing is cooling off over time.
Yes,
if it's cooling off over time,
any
idea that you have of it kind of keeping this magnetic field in a semi-steady state over billions of years is completely gone, because the cooler it gets, the less energy it can feed back.
Bingo! You just nailed it. That's the whole thing. As it cools, it continually supplies more energy, and that energy is lost. But
yes, that's the point.
Yeah, exactly. Over time, like, guess what? Once the core cools completely, goodbye magnetic field. It's gone. Okay? Then that's over billions of years from the current rate. I mean, it hasn't cooled that much comparatively, but like that's where the trajectory that the Earth is going. Once the core cools, the magnetic field is disappeared. Okay? The energy from the cooling core has to continuously be added to the convection currents to power them to create the magnetic field. Like, the magnetic field is created every second. It's induced.
It's again, you need the excuse me, you need the you actually do have to have the reversals to explain the spikes that you see.
I haven't brought up any reversals. You don't need them.
Yeah, you actually do.
There is an effect. Like, once you have a magnetic field reversal, you do have a decline, and then you have an increase, and then it goes back to a normal fluctuation pattern. But there's always that fluctuation pattern. I actually, let me see, Donnie, can I share my screen actually? Let me see.
Definitely, yep.
Right. Let me think. Here we go. Okay. So can you see that? So I actually found this study from the Advanced Earth and Space Science Institute. So they actually had an animation of the last field reversal. And then they have right here, this is measuring the intensity of Earth's magnetic field. Can you guys see this?
Mm-hmm.
So yeah, this is measuring the intensity, and I'll just let this play. So you see like the thousands of years up there on the screen. So this is 43,000 years ago. You can see this is based on actual data that is being empirically measured. You can see the intensity of the field changing. There's the reversal right there. You see it drops way, way down. And then what happens? Oh, wow. It spends a couple thousand years down, and then it starts going back up to where we saw the normal levels before. But right before a field reversal, you start to see all kinds of funky behaviors with the field intensity, and with excursions and everything like that. So, I mean, currently scientists predict that we're actually on track. Here, we can stop sharing now. They actually predict that we're on track for another field reversal in the next 2,000 to 3,000 years, based on the kind of activity that we're seeing with the Earth's field intensity now.
In how many years?
2,000 to 3,000.
2,000 to 3,000. Okay. That's interesting, because you just said earlier that you cannot make any predictions about the
field intensity. Yes.
Yeah.
They're not making predictions about field intensity.
So
there's a
but now we can predict 3,000 years into the future.
Yeah, it's a large margin of error, 2,000 to 3,000 years, and it's, I mean, this is not a precise prediction at all. That they're just saying that in paleomagnetic records, we can see that when you have a declining field strength like this that we see today, and like TRock is correct is somewhat in saying that it's 5% in the last 100 years.
200.
100 years. And the 5% in the last 100 years is what is commonly, that's the consensus among geophysicists. There's a huge amount of doubt in the measurements in the 1800s. I mean, I think most people can understand why. I mean, technology was a lot more primitive in the 1800s to measure these things with any kind of precision. But in the last 100 years, they're precise enough that we can say confidently that it has declined 5% in the last 100 years. But when we look at the paleomagnetic record, we can see that during the times where we see declining field strength like this, we actually see more excursions and reversals happen then. So it's looking like we are due for a reversal sometime in the next few thousand years.
Okay, so let me make one very short point about your graphic that you showed a while ago. That was very cool, by the way. The data for the field strength behind that graphic, nobody's contesting. It's the number of years that you have at the top of the graphic that is being contested. How long did it take for those spikes to go up and down, right? Okay, so having said that, Dr. Russell Humphreys took exactly that type of data and looked at it and looked at exactly the standard equations that you use for electromagnetic decay, and he put 2 and 2 together, and he made a field testable prediction that you can do inside of a human lifetime. You don't got to wait 3,000 years. His prediction was that there must have been very rapid reversals. It's the only way to explain it. He predicted that 3 years before the field study was done by a secular geomagnetic team went out, and all they did was took these, what I described earlier, about a 6-foot section of rock will cool below the Curry point within about 2 weeks or less. And per the comments that those guys made, 2 weeks was actually very generous. It was probably more on the order of 10 or 11 days, probably. Anyway, the point is that they cool fast enough that you should be able to measure reversals inside the period of the cooling of that layer. The outer portions, the outer part of those layers, the outer crust, I'll call it, cools first, and then the cooling continues to the inside. What that implies is that you should see a particular field strength and a polarity direction in the outer portions. And as it's cooling, you start capturing the change in angle and the field intensity both change as you go towards the center. In a 2-week span, they got something like, he says, found a thin layer cooled within 15 days, had 90 degrees of reversal recorded continuously. 90 degrees from the outer to the inner. That is a young Earth type prediction, because you have to have rapid reversals. Reversals are not slow, gradual processes. They're fast because it literally takes mechanical motion to do the reversal.
Yeah. Okay. Well, I'm not familiar with the exact experiment that you're laying out, but I see, I see no reason why that wouldn't happen in either model. I mean, a rapid reversal, the north to south pole switches, that can happen in a few weeks. I don't really see what the big deal is. It's the number of reversals that we're talking about here. Like in one case, these reversals happened every few tens of thousands of years. In the other case, you got like 90 reversals in the span of a week or something like that. There's 300 and something odd reversals in the past million years or so. So if you condense that all to the week of the flood, every couple hours you're getting the north and the south pole flipping. If you're okay with that in your model, that's whatever. But the main point I wanted to make with this subject before we move on is just that there is no reason to assume that the Earth's magnetic field would continue to get stronger and stronger in the past, right? The data that we have in paleomagnetic record, as well as other independent corroborating lines of evidence, like with the beryllium atoms in the atmosphere, shows us that Earth's magnetic field goes up and down in the past in a very chaotic fashion. It's not a nice, neat, periodic kind of up and down. It's not just a steady decline or incline. It's like very chaotic, very difficult to model, but it is absolutely not a disproof of an old Earth.
So,
okay, gentlemen, we're going to have to move on to subject number 2 because we just talked about that for about 40 minutes.
okay.
And so, TRock, you basically started the argument. So I think, to be fair, we'll give Grayson the last word, but I will make sure we get 3-minute concluding statements. So once we reach the end, we'll allow both debaters to wrap up their thoughts and points. So TRock, if there is something you'd like to respond to based on what Grayson just said, maybe note it and save it for there. Okay, subject number 2, TRock.
Subject number 2, erosion rates. Donnie, I can't help it. Do you mind if I try and share my screen one more time?
Sure. Why don't we do this for just the screen share time? Why don't you turn off your camera, save some bandwidth, then share screen, and let's see if that works.
Okay, camera's off.
It doesn't look like the turning off of the webcam has helped at all, because it's now back into lagging stage. So TRock, if you wanted to refresh everything, leave and come back, we'll just keep doing what we're doing. We'll just keep it audio based.
I stopped the sharing, so I guess the audio is still okay.
Yes, but I can see your screen in the bottom right-hand corner, and it's just in a constant load phase.
Which screen? You mean my share screen?
Okay, no, it looks like it's gone now.
Yeah,
so
I've already stopped sharing. It's just that
okay.
Okay.
All right.
Okay. Never mind. We will be talking about erosion rates. Okay. So. Okay, so scientists have estimated, let me back up just there. When you're talking about erosion rates, there's a couple different ways to look at erosion, and I'll use the term types. A couple different types of erosion, the way I think about them. There's what I'll call vertical erosion, and there's horizontal erosion. Excuse me. World. Horizontal erosion would be basically how a flat surface gets lower and lower, or eroded down, and not trying to describe a planar surface remaining planar as it's going down, but basically it's the average height of the continent reducing over time. So that's horizontal, what I call horizontal erosion. Vertical erosion is more like coastlines, where you're eroding inward like this from the ocean into the continent. So 2 different types. Scientists have estimated that some 20 billion tons of sediment are disappearing each year. Eventually, excuse me, the fine material builds up as soft layers of mud on the hard black volcanic seafloor. Surveys indicate that the average depth of all the sediment on the ocean floor is less than 400 meters. Some large areas of the ocean floor have hardly any mud at all. Some rivers are excavating their basins by more than 1,000 meters, or 1,000 millimeters, sorry, which 1 meter equates to about 39 inches of height in 1,000 years, while others move only about 1 millimeter or 0.04 inches in 1,000 years. So the erosion rates vary widely. The average height reduction for all the continents of the world is about 60 millimeters or 2.4 inches per 1,000 years. That sounds kind of slow, but when we do the math, that's not going to be the case, which equates to some 24 billion tons of sediment per year. So a height of 150 kilometers or 93 miles of continent would have eroded in 2.5 billion years. The problem has been highlighted by a number of geologists who calculated the North that North America should have been leveled in 10 million years if erosion has continued at the average rate. The Yellow River in China could flatten a plateau as high as Mount Everest in 10 million years. Okay, so there is that's just a general overview of what's happening in with erosion over time. But you know what? Hold on just a second. Never mind. I'm good.
I already have a lot to say, so.
Okay. I mean, if you need me to stop at any point, go ahead and tell me, and I'll wait.
No, it's okay. You can finish.
Okay. The uniformitarian story is formally stated on a road sign. We're going to talk about Devil's Tower for a minute. It's generally considered to be a conduit of an eroded volcano. More than 300
awesome.
meters.
I've been there.
Have you? Very nice. More than 300 meters of high plain sedimentary rock was eroded, with the tower hardly touched. The uniformitarian story, as formerly stated on a road sign north of the tower, is that erosion of the high plain sedimentary rocks took more than 40 million years. The sign has been replaced, and it now says it took only 1 to 2 million years. However, the erosion of such a vertical tower should be rapid and complete well within 100,000 years. The measurement of river sediment outputs into the ocean indicates that all of North America would have been eroded flat to sea level in just 10 million years. However, this does ignore a range of geotectonic factors. Regardless, a maximum erosion time to level North America is probably no more than 40 to 50 million years. The survival of Devil's Tower is especially puzzling because vertical rock faces, this is really key, are more erosive, being affected by gravity and rock slides and falls. Furthermore, the extensive vertical cracks of the tower would be prone to destruction by freeze-thaw weathering. Freeze-thaw weathering is extremely destructive. While living near the base of the tower, this is a quote from an observer that lived in the area. They say, while living near the base of the tower in November 1954, during periods of frost action at nights, one could hear blocks crash onto the talus. Devil's Tower should have been quickly destroyed, surely in less than 100,000 years. But most perplexing to uniform geologists is that the tower appears to be close to the same size today as it was when it was first exposed. Furthermore, the amount of talus around Devil's Tower is modest, reinforcing the deduction that erosion was both fast and recent.
Yeah, I gotta say, I've been to Devil's Tower, and like, you can see a lot of the remnants of the tower, like around the area, like from it, exactly what you're talking about with freeze drying and peeling off layers of the tower. It was once much wider in the past than it was now. You can see the material that has eroded from it surrounding the area, and also it's igneous rock, so it doesn't erode as fast as the sedimentary rock around it.
I guess, conceptually, I don't totally disagree with most of what you said there, but I will note that per the previous comments that the geologist was making is that if you look at that base, it's not that much bigger than the main column of the tower, not 40 million years worth and not even 2 million years worth. There's just not enough erosion there. Large blocks crashing into the talus during a single winter, that's pretty significant. I wouldn't even argue the point. It's slower than other types of rocks, okay, but it's still quite fast. And if you have large blocks falling off of it, the freeze-thaw cycles apparently are taking their toll on it at a very fast pace. Okay. I'm going to switch gears a little bit, though. There's another really good example. There's a couple named Mark and Louise Roberts. They bought the historic Belle 2, and I think I'm pronouncing that correctly for French. It's French pronunciation. But anyway, it's the lighthouse at Beachy Head, United Kingdom in 1996, located near spectacular 300-foot high chalk cliffs. They turned it into a bed and breakfast, okay? Late in 1998, 2 years later, their dream turned into a nightmare when a large piece of the cliff fell into the English Channel. 4 months later, engineers saved the structure by moving it 17 meters or about 55 feet inland. But they warned it may only be a matter of decades before it needs to be moved again. In 1832, Bell 2 was built about 30 meters or 100 feet from the edge. So think about that. It was built 100 feet from the edge. The engineers moved it 55 more feet, just a little over half that distance. On average, the sea has eroded 1 meter of the cliff every 6 years. In fact, erosion keeps the cliffs white by preventing grass, shrubs, and trees from growing. If the cliffs have been eroding at 1 meter every 6 years since the end of the Cretaceous, more than 10,000 kilometers of coastline would have eroded away. That's like the distance from London to Cape Town, or nearly from Los Angeles to Sydney, Australia.
Are we almost done with the erosion intro?
Almost. There's just a few more little things here. Million years at this rate would see 1,500 kilometers eroded, more than the entire width of England and Ireland. Let me see if I got one more quick thing to do here. See how relevant it is. No, yeah, that's it. I mean, we can stop there. Oh, there was one other quote. I'm not sure where it went.
I'll just say, like, with the cliff, I mean, I don't see any reason to assume why it would all be the same material. Like, you're just saying, oh, it would have to be 1,500 miles or whatever. Why would it all be the same kind of material? Different materials have different erosion rates. But just broadly speaking, there's two things that address this, right? Plate tectonics and something called isostatic compensation. So I didn't actually know what that second one was until I emailed several geologists. I just kind of Googled world's erosion experts. And then I just saw who was publishing what papers. I sent a bunch of emails and I got a bunch of responses. And a number of them brought up something called isostatic compensation, which I thought was really interesting. So whenever you have, this would correspond to, I think you called horizontal erosion, or no, vertical erosion, where they're getting smaller over time, right? So this was really interesting.
Horizontal.
Yeah. So the tectonic plates, that like the continent, oceanic plates, are all floating on top of the mantle, essentially. And whenever the continents are eroded and the erosion, like the sediments, go into the oceans, the entire plate is actually getting less heavy. It's getting less massive because it's losing material. And to compensate for that, it starts floating higher on the mantle. So it's like it's a precise balancing effect. Like you can calculate it. Like you lose X amount of kilograms due to erosion, you raise up X amount of meters. And so there's a complete balancing effect called isostatic compensation. And then in terms of where new material comes from, that's from plate tectonics. So anything you want to respond to with that, or do you want me to explain?
Yeah, your idea of isostatic compensation. I mean, I totally understand the concept. Basically, it's like bailing water out of your boat, or getting the heaviest person out of your boat, and then it comes up higher.
Yeah. And I didn't even know about that until I emailed a few geologists this questions. And basically the answers that I was continuously hearing were mostly plate tectonics, saying, new crust is generated at boundaries of plate tectonics. So someone gave an example of the Andes, and they've measured the rates of the destruction of crust versus the generation of new crust. And they found that it's maintained in a balance. So you get a roughly steady state of new crust being created, old crust being destroyed due to subduction and things. And then erosion, there's a perfect analogy with the bailing out of canoe. As the continents lose mass due to erosion, they float higher and more of them becomes exposed. So there's this nature loves equilibriums. It's kept in balance through those two mechanisms mainly.
So conceptually, I mean, I can't disagree with the isostatic compensation idea, but you've got a serious flaw with it. A couple of them. What you're compensating for is you're raising the continent up. That's one thing. But you've lost all this mass that is in the ocean floor.
Yep.
In order for isostatic compensation to actually solve the problem, what you would have to do is get those erosional remnants that are in the ocean floor back up underneath the continents, not for the sake of raising the height, but for the sake of perpetuating an amount of mass that would keep it above sea level indefinitely.
Well, subduction would be the main mechanism because oceanic crusts are more dense than continental crusts. So whenever they meet, they're subducted below the surface and essentially destroyed. So that's where the extra material is going. And then one more point that I'll just make, that I think the most current estimates are that only about 7% of the current continental crust is older than 2.5 billion years. So we do actually see the majority, like, 93% of all the continental crust, or, somewhere around that, the large majority of the continental crust that was really ancient has been destroyed. It has been lost due to these processes like subduction. But new crust is continuously generated, and that's what compensates for that effect.
It cannot compensate the way you're describing. The Earth being a big round ball, you've got this gravitational effect that's relatively uniform around the planet. Having said that, it's still conceptually no different than if you take a flat pan and pile a bunch of dirt in it and just set it outside and leave it. Over time, that sand is going to all sift down lower and lower and lower. That's inescapable, whether it's the size of the Earth or not. So everything that's getting washed into the ocean, even though you get a certain amount of isostatic compensation for the vertical height, not the mass of the continent, the mass of the continent has to reduce in order for you to get that compensation in height. You've already said that, right? So you cannot put the mass back, otherwise you lose it again. And so let me and this is kind of related to the idea behind Devil's Tower and the other one.
Really quick, the key thing is the density, not the mass, right? What's causing it to float higher is that it's less dense than it was before, because it's the same surface area, but you've lost some material. So if you've added surface area as well as mass, you haven't changed the density. So for example, when two continental plates collide, see, the big difference in your illustration was that if you're just putting a bunch of sand on a ball, there's no plate tectonic activity. With plate tectonics, right, you see things like, the formation of the Himalayan mountains when the Indian subcontinent collided with the Asian plate. Then when two plates collide, they push up and form mountains. So, like, the tectonic activity does completely explain this little problem with erosion rates.
No, tectonics cannot remotely explain it, because if you have actual subduction means something's going down and something's inadvertently or inescapably going up in the process. But that is the problem with your idea. I'm well aware that my example doesn't have plate tectonics in there, but when you introduce plate tectonics, something has to go down and something goes up. So the net effect is not that you end up with more mass above sea level. The net effect is that you're driving the sea level down as well. You're driving the sea floor down in part and raising the sea level. So, and there's another really important part in that too. I don't want to miss this other point, but since we're talking this way, I might as well go ahead and say this. Your model completely ignores common sense collision physics. So when you have two elastic bodies that collide into each other, there is a necessary exponential decline in acceleration. So when you look at, you cited the Andes Mountains as an example, it doesn't matter whether you're talking about the Andes or Mount Everest or whatever. When you see the annual measurements of the height and you see them raise a few centimeters per year, what you're actually seeing is the tail end of an exponential decline in deceleration over time. In other words, you can't take that 2 centimeters a year or whatever it is and extrapolate it back as an average constant rate, because the collision is by definition deceleration and it's exponential.
Well, I never tried to do that, so I don't know why you're bringing it up. But also, I would say that these bodies are not, again, you seem to be omitting the fact that energy is being added to the system. Like the forces that are propelling the movement of tectonic plates do not just go away whenever the plates collide. They're still being continuously pushed together. That's why like the forces that are causing their movement are still active on them even after they've collided. So that's why they continue to push together. And like they would probably decelerate because of that, but like they're still forced together. It's not like these are just like two cars that are driving. Like the engines are still on. They're still, going at it. So
what's the engine?
The main thing is
tell me what the engine is.
Huh?
Tell me what that engine is. What's the engine that's driving them that you said is still running?
The thing that powers all tectonic activity.
What is that?
The energy in the mantle. So
what?
Yeah, the main point I wanted to get across is that plate tectonics explain where new crust comes from, and the new crust is what counterbalances the material that's been lost to erosion. So
your idea of this continually running engine is no. It's no. I don't know where you get this imaginary energy from the core driving horizontal motion to create vertical uplift. There are literally, have you ever taken a physics course, a college level physics course?
Yes.
Did you ever have to draw free body diagrams?
No.
Well, I would encourage you to take a college level physics course where you're drawing free body diagrams. The amount of force that you need in this direction to create a 90-degree vertical is huge. You don't get that from some thermal idea about what the core of the Earth is putting out, giving to the continents. The reason I brought that whole thing up about the exponential decline and deceleration is because when you draw your free body diagrams, you find out that the amount of force is ridiculous in this direction to get just a little bit of motion in that direction. And the Earth's core is not doing that.
Is your theory then that geologists are just not aware of free body diagrams and physics? So you think that this thought just hasn't occurred to them, or what?
No, my theory. Let me explain my mechanism behind what you see today. Ignore what I think other scientists.
Well, I'm not asking for your entire worldview about explanation. I'm just thinking.
I'm not. No, I'll just. It's very quick and I'll explain. It's super simple. This horizontal movement that we got was probably from something like like a very sudden seafloor collapse, and it drove continents to move this way. Now, I sit and did the physics on this, or I did the energy calculations. All you have to do is approximate a mountain range, for example, as a triangle. And so a triangle, its centroid, its mass centroid is 1/3 of the height of the triangle, right? So all you have to do is just approximate the mountain range as a triangle, and then use the potential energy equation and compare it to the kinetic energy equation of the motion of the continent. and I did this on my own, and I came up, interestingly, with almost the exact same numbers that people like Michael Ward and John Baumgartner and some others did, and that is you need the continents to be moving at about 2 meters per second. And to put that into perspective, that's about like a medium to brisk walk.
Yeah, but again, you're completely ignoring the things that are powering the movement of the continents, which don't just go away. These are not free bodies. Like they are being they're being supplied with energy, with like things like sea floor spreading. Like they're being driven forward. Like they're not just going off of their own kinetic energy. Like there's more energy to account for in your equations than just purely the kinetic energy of the plates. But like largely, I just want to say, like, do you think that geophysicists and geologists this has not occurred to them? Like, you think that they just haven't done the equations, or do you think that this is a conspiracy and they're covering up these equations? Like what do you think? Like, why hasn't this occurred to the field of geology? Like, if what you're saying is true.
I hate to say it this way. First of all, no conspiracy, not remotely trying to touch the idea of a conspiracy. I don't think there's any conspiracy like that in that sense. Zero. That's not what I'm saying. You're saying, why hasn't it occurred to geophysicists? Here's the huge difference in this debate. There is real-time physics, and then there's the storytelling of evolution. When you're over here in the storytelling of evolution, the explanations are not generated by real-time physics. If you go read the actual scientific literature that does not address evolution and origins, deep time and all that kind of stuff, if it's not addressing that, they're going to say pretty much the same things I'm telling you today.
So, I mean, we can observe mountain ranges forming and being pushed up higher today due to plate tectonic collisions. So, I mean, we can observe this. The Himalayas are getting taller.
Again, an exponential. What you're seeing is a decline, and what I'm predicting, I'll be very specific about this, but I'll be honest with you, you can't really, you won't live long enough to actually see this happen, just like your 3,000 year prediction. What I'm telling you is, if that rate of growth is 2 centimeters a year, two things are immediately obvious to me. Number one, you're only talking about the mountain range, not the entire continent. And number two is, over time, that 2 centimeters is going to become 1.9, 1.8, 1.7. It is decelerating because of the friction forces and the direct impact that you're experiencing. You're not shoving a watermelon through a brick wall. It has to decelerate over time. There is not enough energy in seafloor spreading or the core thermal convection currents from the core to account for any of that.
Okay, well, I don't know if you've done the math on that. I think you haven't, but this is a problem with a lot of your mathematical equations that you've used tonight, is that I think that you're not accounting for all the variables that are relevant. I think you're simplifying things too much to use mathematics that you're familiar with, like kinetic energy and triangles. But I think that if you were to try and familiarize yourself with the literature of plate tectonics, see what math is actually being used to describe this stuff, I think maybe you would see that it's a bit more sophisticated. But largely, that's just what I wanted to communicate, is that plate tectonics create new material, new crust that compensates for erosion effects. And that's the main point that I wanted to get across.
Okay, so one more thing I'll say real quick, and we can move on to the next one. Have you ever taken a course in mathematical modeling?
In mathematical modeling specifically, no. I've taken up to differential equations.
Okay. In mathematical modeling, there are two basic approaches. You can take the complex approach that you're describing. If you know the inputs, you have to know the inputs to be able to do that. But you can take the more complex version where you've got all these different parameters that you've got to plug in, and you can do your model that way. The other way to do it is to simplify the model and simply widen the parameters to be able to account for all those other things you described that you said I'm not accounting for. I know how to account for them. And a real good example is where Dr. Robert Carter did this phenomenal job of modeling population growth among people and animals. I think people was his specific topic, and that's what mine was. He did exactly what you're describing. He put in all types of parameters that had to do with age, number of children that you bear, how old are you when you start conceiving. He put in all those parameters and came up with a brilliant scientific model that is very concise, like what you're describing. I took the other approach. I took the simplified model, but I know what you're saying is true. Those other factors, they do matter. How do I compensate for them? I broaden my few parameters that I do have so that they can account for that too. So what I do instead is give best case scenario, worst case scenario. I'm bringing this specific example up because I did this exercise independently of Dr. Robert Carter, and I came up with the exact same ranges that he did.
Grayson, did you want a quick final word on subject 2, and then we'll move to subject 3, or do you want to move right to subject 3? Up to you.
I pretty much had my final statement in the last one. I mean, mainly plate tectonics, isostatic compensation was something fun that I learned about this topic, but mainly plate tectonics fully explains why erosion rates are not problematic for an old Earth.
Okay, so subject 1 was a magnetic field decay. Subject 2 was erosion rates. And we are now moving on to subject 3. And to the audience, I am all caught up on your questions. And so, as always, excellent questions. We have a very lively chat, as it has been a great debate so far. So, TRock, topic number 3, floor is yours.
Okay, topic number 3 is lunar recession. This is what I think is one of the most interesting ones. And I actually fortuitously, I think I may have consciously did this whenever we were defining what our 5 topics were going to be. But I deliberately put, I think I did, lunar recession immediately after erosion rates. And we'll develop exactly why that is as we talk about this. But think of the famous coin funnel that you might have seen at a place like McDonald's, where you drop a coin in and it spirals around and around until it gets down towards the bottom. And what you notice is that the coin speeds up, of course, as it gets down to the bottom. So that is essentially the general idea. I'm well aware there's significant configuration differences and whatever, but that's the basic idea behind lunar recession, is that as you wind the clock back, it's kind of like the coin funnel example going forward. The moon necessarily gets closer and closer to the Earth. And the reason is because in real time going forward, it's drifting out further and further away. So we call it recession because we're winding the clock backwards to see what happened 100 million years ago, 500 million years ago, that sort of thing. And so one of the things you notice in the coin funnel example is eventually it gets to the bottom and it drops out. And so I'll say that's roughly comparable to the Roche limit, even though the Roche limit is actually something different. The Roche limit describes what the closest distance the moon could be to the Earth before it's moving so fast that it basically tears itself apart. So the other example I liked to look at, and I apologize, I really hate that we can't share the visuals here, but orbiting magnets. The general idea is very similar to orbiting magnets. You can hypothetically take a uniform geometry magnet and use it to represent like the Earth in a stationary axis, and then take another magnet or even a non-magnet, any ferrous material that's attracted to it. And the point is, you can spin one or the other relative to the other one at a certain speed, and for the strength of the magnet, it will hold it in orbit. Unfortunately, it won't do it indefinitely. But think about that. You have one magnet here and the other one, they're trying to pull themselves together, but the actual motion around is like this. The actual motion around it is what's keeping it from just slamming in together. So you've got all this kinetic energy to counterbalance the force of attraction between them. Okay, so that's the general idea behind lunar recession. Now there is a particular equation for describing the recession rate. And what it looks like is, give me just a second, I'll pull this up and make sure. Here we go. What it looks like is there's a number that's represented by the letter K. And what it is I'll call it I don't know how to, it's basically, it's roughly equivalent to what you'd call a decay constant in radiometric dating. But it is K is equal to 1.2 times 10 to the 29th kilometers to the 7th power per year. In other words, how many trillions is that? That's 2 trillions, and add another 100,000 to that. So it's 100,000 trillion kilometers to the 7th power per year. That's what I'll call the quote unquote decay constant, or the recession constant. And then there's an integral equation that you use to basically translate that to an actual formula that you can just crunch the numbers in. That formula crunches down to r to the 7th, and r would be the distance between the moon and the Earth from their centers of gravity. R to the 7th divided by 7 times K, that 1.2 times 10 to the 29th number I gave. Okay, so with that, you can calculate backwards, and you can see, and you can basically predict, so to speak, in time where the moon should have been relative to the Earth given a certain number of years. As it turns out, 1.4 billion years, and you've already crashed into the Earth at that point. And so everybody's familiar with the famous gravity is proportional. It's the inverse square law. If you're familiar with that. So the closer by distance that the moon gets to the Earth, the gravity increases by a factor of squaring, right? So what does that mean? If you wind the clock back 6,000 years to the biblical time frame, there's so little difference you can't hardly tell. 6,000 years is not enough to affect anything, but 1.4 billion years is. So what I wanted to do was I wanted to go back and look at what did the evolutionists think that the globe looked like 100 million years ago, and what did it look like 500 million years ago. I picked those values specifically because you don't have to go all the way to 1.4 billion years before you start having serious problems. So what this boils down to is, as the moon approaches the Earth, going backwards in time closer and closer, and the gravity is increasing. So if you get, for example, 10% closer, the moon is about 240,000 miles away from the Earth. And if you come in 10%, you've only come in about 24,000 miles, right? 10% closer represents a gravitational increase of like 23%. I've actually got this on a chart here, so I should just be reading it directly off of it. But you can, and there's another weird thing that happens too, not totally weird, it's just normal physics, but if you don't think about these things, you don't realize what the impact of implying billions of years really is. But the number of days that it takes for the moon to go around the Earth also decreases. This is related to the idea of conservation of angular momentum. It's a little bit, it could be a little bit confusing, the terminology, but basically what that means is the linear speed of the moon is constant. And so as you're coming in closer to the Earth, the linear speed stays the same. That's what the coin example was for. The linear speed is actually the same. It's the angular velocity that has to increase in order to keep the linear speed the same. So that's why the days get shorter and shorter as you draw back in time. So what I did was I kind of plotted this out, and what you get is today you're at gravity, relative gravity strength is 1.0. Your average lunar cycle is about 30.4 days. If you get 10,000 miles closer, your relative gravity becomes 1.1. In other words, it's 10% higher. And your number of days drops down to 29.2. At 220,000, you're at relative gravity of 1.2. In other words, 20% higher. And your number of days in the lunar cycle drops down to 27.9. So what I find most interesting about this whole thing is, again, you don't have to go near the 1.4 billion year timeline to start seeing a problem. It happens way before that because of the amount of gravity. So there is that you end up with a problem with the tidal kinetic energy as the moon comes across and draws tides towards the continents. You have tidal energy. The tidal kinetic energy is described by the simple Newtonian physics, E equals 1/2 mv squared. Now, here's the thing though, the percent of mass of the tidal bulge is going to increase proportional to the gravitational increase. So if the gravitational increase is 20%, the mass of the tidal bulge also increases by 20%. The tidal velocity increase is related to the actual velocity increase of the moon, and that's the radial. The tidal velocity as it's coming across this way is directly related to the radial velocity of the moon. So you get these days, they're getting shorter and smaller and smaller number of days in the cycle. You're raising the tidal bulge. You're increasing its kinetic energy as it hits the continents. What does this all mean? It means that all the discussion we were having about erosional rates a little while ago, you're driving them through the roof exponentially. And it's necessarily exponential because of the inverse square law. And so what I did was I went back again 100 million years, 500 million years. 100 million years ago, you can go on Wikipedia and you can see what they call the Western Interior Seaway, where it literally looks like it kind of dips through the Gulf of Mexico and from the Pacific side, and the seaway kind of cuts in between the middle of the North America in the United States.
1 minute, TRock.
Okay. And so what you have at 100 million years ago, you have this crazy problem with sea levels in the conventional literature are so high, but the gravitational increase from the moon is also really high. Your erosional rates are driven through the roof, and basically you would never get continents today if that were true. So I'll stop there, and we can go on a little bit further, but there's another interesting equivalence to make there with 500 million years ago.
Okay, well, I'll just ask if maybe you could be a little bit more concise in making your points, or maybe like being clear about this is what is limiting the age of the Earth, because you talked for a long time there. You brought up a whole lot, but I'm not exactly clear. Where did you get that 1.4 billion number from? What was that equation that you did?
So that is the standard open literature physics equation to describe how the moon is moving away from the Earth, because it's a function of the gravity, the gravitational attraction between the two bodies. It's a function of the distance between them.
Yes.
And the reason it's out to the 6th power on that K constant that I was describing is because it's also a function of the tidal bulge changing over time, right? So
yes, so ultimately, like the tidal forces are what is supplying the energy for the moon to continue to move away. That's ultimately where the energy is being compensated.
It's sort of, it's kind of related to, like, if you tie a block to a string and run it around like that. If you pull on the block, you speed up, or pull on the string, you speed up the block, right? So you're inducing tension and speed it up. Of course, in lunar recession, where it's receding away from the Earth, the opposite is happening. You're letting the thing go a little bit slack, so your deal can actually fly away from you.
Not exactly. I mean, it is the tides. I mean, this is according to NASA. The energy compensation that is fueling the moon to move away is from the tides. But that point is neither here nor there. So you're saying that in your equation that it is accounting for the inverse square law. So it's accounting for increased gravity, which would slow down the rate of recession, right?
Over time going forward, yes. Yeah.
So like, no, not going forward. The rate of recession increases over time because the strength of gravity decreases with distance.
But yeah, that's what I said.
Okay, so you would agree with that?
Yeah.
Okay. So
say that one more time, just so I can make sure I was exactly.
The rate of recession that the moon is moving away from us increases over time because the gravitational effects on the moon, like what is keeping it bound to Earth, decrease with the distance that it recedes.
And you're talking about going forward in time.
Yes.
You're exactly backwards. The moon slows down its rate of recession as it gets away because the gravitational force between them is less.
So it would increase its rate of recession, yeah.
Decrease.
Look, the gravity is what is holding the moon close to us.
Okay.
So as there's less gravity, as the moon gets farther away, there is less force keeping it closer, therefore it recedes faster. I mean, this should be very intuitive to understand.
No, unfortunately, you're exactly backwards. You're exactly backwards. It slows down. It's moving slower and slower away. It's not strictly a function of the gravity.
Think about this for a second. If gravity just turned off, zero gravity, the moon would go flying away at a very, very fast speed.
Okay.
If you agree with that, then you should agree with that the less gravity that is factoring on the moon, the faster its recession speed should be.
No, I'm sorry, but this is an actual physics problem, and nobody in the open literature would agree with you, because the gravity gets weaker, but the tidal energy gets weaker as well.
Yes.
And you have to conserve angular momentum in the process. What that means is, as you get further away, the number of days of rotation of the moon around the Earth is going to increase. The number of days is going to increase. Its linear velocity, as you measure it in terms of how you think about a straight line, even though it's going in a circle, its linear velocity is constant. The gravitational force is weakening, but what you did was kind of an equivocation fallacy. You flipped gravity completely off instantaneously to describe how it's going to fly away from the Earth, and I can't disagree with that because that's totally true. My example of the string, as you let slack into the string, I'm going in a horizontal plane.
What actually represents the weakening of gravity.
What actually happens in that specific example is your weight out on the end of the string is going to start falling, right?
Yeah.
But its linear motion its linear velocity is going to stay relatively constant until it's interrupted or declines by reason of friction in that example. But we don't have friction per se in the Earth-Moon system.
By linear velocity, are you talking about like its velocity of recession?
No,
okay.
I'm talking about its circular path, because you have to understand the difference between angular velocity, which is how many degrees it moves over time, versus linear velocity. It's a circle that it's going. It's technically not a circle at all, and that's another problem. But anyway, it's an elliptical orbit. But either way, we'll pretend for the sake of argument it's a circle. And that linear velocity I'm describing is its actual travel speed along its path.
Yeah.
Which is different.
Well, I really don't see the issue of why you're getting like 1.4 billion. I mean, the rate at which the moon recedes is not constant.
That was the point. It's related to the sixth power of the radius between them. That's what causes the problem. It's not linear.
So the rate of recession slows down as you go back in time.
No. You're saying the exact opposite again of what standard physics tells us.
I don't know.
Standard physics tells us that if you look at the graph, essentially what you're going to see is this graph looks like this, and it looks somewhat linear, but because it's related to the sixth power of the radius, all of a sudden it hits this point, and I could tell you specifically, it looks like it is at about 250,000 kilometers. What would that be in miles? That's a little over half, so it would be about 120 something thousand miles from here. But anyway, about half the distance between here and there. All of a sudden, that recession problem, winding the clock backwards, causes it to dive steeply into the Earth because it's the sixth power.
Well, there are two broad ways of which the moon can lose its energy, right? It can recede, or it can before it's tidally locked, it can get closer and closer to being tidally locked. So when it gets to a certain distance that's close enough, the way that it would be losing its energy would not be through recession. It would be through tidal mechanisms until it's tidally locked. And then once the moon is tidally locked, then it begins to recede. That's what the physics shows.
Okay, so you have a minor point there, but you got a major problem with it.
Well, this is according to NASA. So
you're talking about transferring the energy in the rotation of the moon that actually is tidally locked now, right?
Yeah.
How in the world are you going to demonstrate that with real physical evidence some 4 billion years in the past or whenever they think it became tidally locked? How are you going to demonstrate that?
I mean, you would just demonstrate it with physics, the mathematics, modeling. You would show that obviously during the creation of the moon, right, it would not have been created.
So you can just write you up an equation and go, poof, I've solved the problem, and tell everybody we got evidence.
An equation that's describing the process by which the moon would become tidally locked. And then we know that once it's tidally locked, then it begins to recede. So it hasn't been receding the whole time. It had to be tidally locked first.
Only if you insist that there had to have been billions of years. Otherwise, you don't need that as a solution at all.
All right, but it works with the physics.
Actually, it don't. And I'll make a little prediction for you.
Okay.
So what I'm suggesting is that at 10% closer to where the moon is today, 24,000 miles, is a huge erosional rate problem. And that 24,000 miles happens... I want to say, what did I figure out? It happens somewhere around the 450 million years ago or so. I'm going to predict that if you go into the open literature and find where anybody's talked about this tidal locking event, they have it well before 450 million years ago.
Yeah, definitely would. I would agree with you there. I mean,
And
I'm getting this information mostly from NASA. Like
so the point is that you have a problem long before 500 million years ago.
Yeah, I don't think that we have that problem, though. I have come across no one that has shown those numbers that you have, and I am very skeptical of your equations that you've been using, since in the last 2 points that you haven't been using the appropriate equations for the scenarios.
That's funny considering you don't actually understand them, but again, this is the same thing I described earlier. You're going and looking at evolutionary storytelling, and I'm going and looking at real physics. If you go look at real physics, you will find what I'm saying.
Oh, so NASA's not looking at real physics.
NASA isn't built around what happened 100 million years ago. NASA is built about building satellites and spaceships and stuff today.
Yeah, that sounds like real physics to me. You'd think that they would be using real physics.
And you're not separating the difference between building real-time technology and imagining something in the past. NASA can't build a spaceship because the moon tidally locked 1.8 billion years ago. That's got nothing to do with it. So you don't find the equations I'm talking about in the conversations about something that happened 1.8 billion years ago. They don't go together. That's why you're not finding them together.
So where do you find the equations that you're talking about?
I just told you. Go
You
to the open.
You gestured broadly to the open.
Go. So I'll be a little more specific. If you talk to somebody like Michael Ord, who was a climatologist at one time, what I'm describing is directly relevant in modern climatology, because you have to understand the effects of the moon on the climate. Mm-hmm. So that's where you will find it. It's not, and they won't have any pretext to evolution unless they've got some sort of weird agenda. But if you're literally talking about real time, how do I predict the weather tomorrow? Mm-hmm. That's where you find the conversation and the formulas that I'm talking about.
So you're finding the formulas from this Michael Ord guy who's a climate scientist.
Nope, I didn't say that.
Okay, well, if you can find any actual astronomy or physics that is like any literature that is verifying your use of these equations and the results that you're talking about, I'd be interested in seeing it, because I looked through the physics journals for this topic and I didn't see any use of these equations. I see the math that supports tidal locking and then recession of the moon, and that fully covers it.
I'll tell you what, I will see if I can find the source for that specific equation, and I will see if I can get it to you. I can get it to you by email or whatever your preference is. I don't know.
Sure.
But if you would like to see where that comes from, the open literature, I would be glad to share that with you. I don't have my screen share deal enabled right now. I can see it on my own screen, but it's not going to do you a whole lot of good.
Okay. Well, what journal was it published in?
For that, I'll be honest with you, I don't know off the top of my head. Okay. But I used, and full disclosure, I used a secondary source, but it's that's
Creation.com.
So it's a complete non-issue, because if you go to my what I'm calling secondary sources, they provide you, and you should do this. Since you like to do your own science research, I highly recommend you do this, because most evolutionists do not seem to be familiar with the creation model at all. I'm not trying to project that on you, but I know that's such a common theme. What I would suggest for you is to go to creation.com, see if you can find the information, but I can tell you with all certainty that they are very good about documenting the open science sources. So you can, as a secondary source, you can go through there and find them. I do have a lot of original sources.
We might have a different definition of what is a good quality of documenting sources. I recognize that they have a bibliography. I've read several creation.com articles, but I don't think that they do a very good job of accurately representing the data that they talk about. It seems like they're definitely trying to push an agenda, and they will misrepresent any scientific literature that they can in order to do that.
Well, that's a lot more like an ad hominem than legitimately addressing the science. What I would suggest, instead of taking that approach you just did, go and look at the sources that they offer at the bottom, because I do this, and I have literally had evolutionists provide me with sources to what their trusted sites are, and they don't say what the evolutionists say they do.
Okay.
And
I can't speak for others, but
we're talking about like geophysics, science. That's a major journal.
Yeah.
If you don't trust those,
yeah, well, I would trust major scientific journals. What I don't trust is creation.com. So I feel like oftentimes people will read a creation.com article and they will trust the authors of that article, that these authors have read and understand the sources that they're talking about in the secular journals. And oftentimes, pretty much every time when I have actually read the article, I've gone to their sources. Their sources are not saying what they say their sources are saying. Like, they are misrepresenting the secular journal articles. So I've seen that almost every creation.com article does that.
That's funny. My experience is the exact same, going the opposite direction.
All right.
But I guess let me summarize some things real quick on these, because you asked this one.
I was just going to say, yeah, TRock, if you wanted to summarize your points now, and both of you wrap up your points on subject number 3, Lunar Recession. Been very thorough so far. Definitely a technical debate. And so I'd recommend, I know it's the kind of debate you're going to want to watch a couple times. And so TRock, go ahead, and then we will transition into subject number 4.
Okay,
and
so
for subject 4, can we do the soft tissues for dinosaurs? You don't want to? Okay. Well, we can do it in order.
It's just that there is a direct correlation, like I just showed. There's a direct correlation between erosion rates and lunar recession, and there's also a direct correlation between carbon-14 and dinosaur soft tissue. That's why I kept the original order I sent in the email, because it just, whether it was fortuitous or I intentionally did it, the order happened to work out quite well.
Whatever's clever.
Okay. So let me recap something super quick for you, because you asked a specific thing about how does that limit the age of the Earth in general. So the erosion rates by themselves limit the age of the Earth to under about 10 million years per some of the information I was reading a little while ago. How does lunar recession limit the age of the Earth? Well, in standard apologetics, they'll cite that 1.4 billion number. That's the point of crashing. Realistically, when you combine the actual physical effects it has on the surface of the Earth, it limits that 10 million years even more. But if you take it all by itself, it causes a problem with well within 500 million years. But the tighter limit is from the erosion rates themselves. It just gets worse when you include the lunar recession problem. Okay, so carbon-14. I'll switch a little bit on that. We already talked about magnetism. I will tell you that one limits the age of the Earth the tightest, actually, to about 10,000 years. We can talk about that again later if we want. But radiometric dating for carbon-14, I'll just say it up front before we start. It's going to limit the age of the Earth to, I'm going to say 50,000 years max. But you could argue 100,000 if you wanted to. It's neither here nor there to me, but 50 to 100,000 years maximum. And then dinosaur soft tissue. Here's another one where I kind of take slightly different path from mainstream Christian apologetics. They will typically cite the maximum decay allowance for soft tissue to be, 1 million years for collagen or something like that. I'm going to demonstrate that's actually not the case if we can get that far. It actually is limited much, much below that. I'll say 20,000 years, probably, just throwing a number out there, but there's absolutely no way you can get past 20,000 years with dinosaur soft tissue. Okay. Now, before I start, if you care to reflect on any of that, go ahead.
Well, yeah, I mean, obviously, I'm going to take the opposite stance. Collagen can last a really long time when it's highly cross-linked. So. Okay.
So we should talk about that later. Yeah. I was going to do radiometric decay.
The dinosaur soft tissues actually prove an old Earth. That's where we're going to conclude.
If you mix and match worldviews, you can come to that conclusion.
No, they debunk a young Earth. Like what we see with the dinosaur soft tissues completely debunks a 6,000-year Earth. So that's going to be it. The first point of evidence that I'll make for the old Earth will be the dinosaur soft tissue.
Okay.
So are we doing, just to be clear, for myself, the audience, subject number 4 is radiometric decay, you said, TRock?
That is specifically carbon-14, yes.
Carbon-14, okay. All right, go ahead. Let's start. Topic number 4 begins now.
I think I'm going to abbreviate this one a little bit, though, because there's a lot to it, and I want to abbreviate it down to the point where it actually becomes relevant to dinosaur soft tissue. So carbon-14 has a half-life of 5,730 years. Okay. What that means effectively, and again, I actually did the math. You can do this, do it in an Excel sheet. You can calculate the mass of the Earth and pretend, and what I did was how many atoms of carbon-14 constitute the equivalent mass of the Earth. Like the entire Earth is made of carbon-14. And then you can just use the standard half-life decay rate. And what you find out is you are down to the very last atom in less than 1 million years. Now, if you just jump past that and go to the mass of a human being, or the mass of take a very large dinosaur that, let's say, hypothetically, it weighs 80 tons or something like that, you can calculate the amount of carbon-14 it might have had in its body, and then start with that many atoms and run the math. And of course, you come up with way, way less than 1 million years. You come up with something that looks more like, and I did this on one of my other slides, but you come up with, let me see if I can pull that in here real quick, and I'll tell you what those numbers were.
So you're not going to use bones in this illustration, are you? Because you can't carbon date bones.
That's kind of funny. All I'm really demonstrating here is if you start with X number of atoms that you would expect in a living body at the time of death, that many atoms decays away 100% down to the very last atom within some number of years, right?
Yeah, I'll agree with you on that for sure. No argument here.
Okay.
Like what we see with C14 in dinosaur bones or any kind of thing that you want to bring up like diamonds that's new carbon-14. That's not original carbon-14. So carbon-14 is continuously being created in the atmosphere. So and in other sources as well.
Sure.
So that's the whole rebuttal basically.
Okay. It's not going to make a whole lot of sense here in just a minute. Okay, so human body, we're going to say I used 80 kilograms. Human body has approximately 3.8 times 10 to the 14.
TRock, I already agreed with all this. Like, I agreed with your calculations that you're going to run out of carbon-14 after a short amount of time. I agree. Let's move beyond that.
Okay, so just for the sake of the audience, what you get out of that is, hold on just a second. I'll tell you what
I don't think it's really relevant for the discussion, though. That's what I'm saying.
Okay, fair enough. So I'm going to have to jump forward to the part of dinosaur soft tissue to explain why one of the reasons your idea is not going to work.
Are we combining like the points 4 and 5 then?
Sort of. Like I said, there's some overlap, and that's why I kind of strung them together. But I'll try and stick more specifically to the carbon-14 thing. It's just that when you do dating, it becomes relevant. So I think what I understand you were saying, new carbon-14 produced in bones.
Not produced in bones, incorporated into bones, because when bones are deposited and during the fossilization process, they go through something called recrystallization. So the actual bones will break down and then recrystallize using elements in the environment around them, including carbon-14. So they actually are incorporating new carbon-14 into bones as part of recrystallization.
Let me get you to clarify this point on that. Are you describing 100% permineralization?
No. So this is called bone recrystallization. So this is a known phenomenon. This is why bones are not typically used to carbon date anything, because it's known that bones will recrystallize like in months to years, or like that they will recrystallize like continuously and get carbon-14 from their environment, rather than preserve the carbon-14 that was originally in those bones when the organism died. So bones are not used for carbon dating typically.
Okay, I understand what you're saying, and I would have predicted a couple years ago. I would have predicted that that is a bunch of baloney. Just to be perfectly honest with you, I kind of did a couple of years ago before I even knew what kind of technical information was out there. And the reason I predicted that was because common sense should tell you that in order to get carbon-14 from the surroundings of the bone into the bone, you need a transport mechanism. Right?
Oh, you need a diffusion mechanism, and you need a recrystallization process that is incorporating this carbon-14, which is both explained.
But it has to move the carbon-14 atom from there to the bone.
Yeah, diffusion.
Diffusion.
Yeah.
What are you calling diffusion?
That is the movement of atoms.
At strictly an atomic level, or are we talking
Molecular.
about at a molecular level?
Yeah.
So you're talking about minerals.
It can be gaseous, it can be mineral in nature. Diffusion applies to all of these things.
Okay.
Like, this is known. This is why bones are not used to carbon date. Even recent bones. Like even recent bones are not used for carbon dating because of this process.
So the reason I would have predicted this, whether it's correct or not, is irrelevant. It was kind of a gut check for me. I was sitting there thinking, okay, how do you get to carbon-14 from here to inside the bone if it's contamination? Well, pretty much the only mechanism that you're going to get it there is through water transport.
It can be water, it can be gaseous, it can also be bacterial. So bacteria will oftentimes live within bones, like that are in the ground. And bacteria are living organisms that obviously respire. So they're breathing in new carbon-14 and depositing it in those dinosaur.
So I can talk about the bacteria thing, but that's kind of a rabbit trail. So I'm going to stick to the main line here about how you allegedly regenerate carbon into the bone. And what I'm suggesting is about the only common sense mechanism that contributes significantly is water transport. In other words, per your comment, molecular level transport of minerals down through the bone. But that is the very process that defines permineralization. Now, one of the big problems I have with what you described is that there are a huge number of bones, dinosaur bone era bones, that are found as identical to modern bone, just dried out. And so there's a funny geological test that they do in the field where they put their tongue on the bone to see if it's actually bone or if it's mineral. If it sticks to your tongue, it's a bone. If it does not stick to your tongue, it's a mineral. In other words, fully permineralized. Okay, so my prediction from a long time ago, notwithstanding, because like I said, I'm willing that I was completely off base on that, although I still to this day don't think I am. I stumbled across very fortuitously. I actually went looking for something, but I came across this particular study that was done, and this is where the crossover comes between carbon-14 dating and dinosaur soft tissue. Some folks in Germany and China got together and did a study and had this big conference about this very subject, carbon-14 in dinosaur bones. And so what it boils down to, and I think this is one where I should probably actually read from some of my notes here instead of skipping them. Hadrosaur femur bone from Glendive, Montana, 5.59% of modern carbon. Allosaur bones from Colorado, 2.02% of modern carbon. Triceratops bone from Montana, 2.16% modern carbon. At 5:20 of this particular video that I was watching, this guy was giving his presentation at this big science conference in China, I believe, but it was a coordinated effort between some Germans and some Chinese entities. But anyway, 5:20 of the video, he says, you see that all range from between around 0.7 to 6.5% modern carbon. Okay. At 11 minutes in the video, he's got this chart up that shows a lot of really interesting detail. He says low probability of contamination because of, and that's kind of the title of his slide, is low probability of contamination. So this is where your idea of you somehow got regenerated carbon-14 is, it's just blown completely out of the water with this particular study. Percent modern carbon concordance of organics and extraction. If percent modern carbon of organics stemmed entirely from contaminant, then we would expect intermediate percent modern carbon. And in other words, it wouldn't be at a constant rate. It would be at some kind of erratic rate.
Unless bone recrystallizes, which it does.
Okay.
Like, this is the whole process that I feel like you're just ignoring here.
No, I'm not.
Recrystallization of bone accounts for this.
I'm not. And there is a scientific method that helps you delineate between what you're describing and what's actually happening, because what you're describing is not what's actually happening. But there is a method in science to help figure this out. And that's what I'm describing here. Low probability of contamination because of percent modern carbon concordance between AMS and beta MS, small sample size and large sample size, inhomogeneously distributed contaminant would be found. So they used two different methods and found that the percent modern carbon was very uniform through any given sample.
Exactly like we would predict with recrystallization.
Then why do a bunch of scientists say that you should find this inhomogeneous distribution?
If it was contamination from the environmental source, that's true. But if it's from a result of recrystallization, we would expect
recrystallization is contamination.
It's not.
Again, how did you get that in there? It was through a contaminating source.
It was incorporated by the bone.
Okay. So 11 minutes of the video. Again,
bone is not used to radiocarbon date for this reason. Even a few months or years, like within 10 years, this is going to happen. Recrystallization is an ongoing process. The actual chemical structure of bone changes after it's deposited. That's why bone is not good for carbon dating.
I'm not done with the method that they went through to determine this. So I think you're a little premature still. Okay, again, low probability of contamination because of ... Matrix on Triceratops had PMC of 6.4, which is huge contamination needed to produce the sample of percent modern carbon. In other words, if your idea were true, you still could not get anywhere near 6.4% of modern carbon. Point number two, again, low probability of contamination because of the same pre-treatment procedure delivers percent modern carbon for many plant fossils. This would have occurred in these plant fossils too. And that's a direct
There's no bones in plants. Plants don't have bones.
So they can't recrystallize, can they?
Exactly, yes.
But they have the same carbon-14 stats in them.
If they're contaminated, but I don't think that they are. I don't think that what you're reading is accurate.
The percentage of carbon becomes smaller the further we get from the fossil. That's one of the reasons why there's low probability of contamination. Results sorted by PMC. This was probably, to me, what I got from the video, the guy giving the presentation found this to be the most striking piece of evidence in this whole thing. Results sorted by PMC. Inside each group, a very good PMC concordance is obtained. So what that means is he actually had, and so this is, again, this completely refutes your idea of this bone. He was looking at specific proteins and different types of soft tissue elements, and they were identified as soft tissue, not bone. And so what he said was, after he sorted it by the percent modern carbon, what you fell out was this very natural looking line of all of, say, collagen fell here, all of whatever, different type of soft tissue fell here, all of another one fell here. They were very neatly grouped together in soft tissues, which is not what you would expect at all through a random contamination process.
Yeah, that makes total sense based on what I've been saying.
You've been talking about bone, not soft tissue.
Yeah, I know, but the different kind of material like bone would
it's not recrystalline
carbon-14 at different rates based on the material. That makes total sense.
Soft tissue doesn't go through recrystallization. It by definition has not.
Yeah, that's why it has less C14 in it than bone.
That's not what this said. 6.4%. That's
So
a
what are you
soft
reading
tissue
from?
number. Huh?
What are you reading from?
This was in the 11 minutes of this video. And I'll tell you, I mean, I can read off what the video is. You should go watch this. It's on YouTube. It was video slash or youtube.com/watch?v=QBDH3. I don't know what that character is. It's like the vertical deal, not an alpha character. 1UJPQ. Anyway, it's just some random entity. And I couldn't tell you whether they were creationist or not. I was only interested in the data that they came up with. Anyway, so I said conclusions and suggestions for further work. 14C in dinosaur bones detected, which is likely endogenous. Conclusions and suggestion for further work. Results can be explained by rapid horizontal strata formation as observed in laboratory experiments with moving water. So when he got to the end, again, I think what was most striking to him as an individual seemed to have been how these percents seem to match up perfectly with each different type of soft tissue that was found.
Mm-hmm. Do you think that maybe have a slight something to do with that the percent of carbon atoms are different depending on tissue types?
Well, there's yeah,
They're
I
made
mean,
of different molecules that contain different amounts of carbon in them inherently.
yeah, that exactly makes my point though.
So yeah, if there's
It's
a soft tissue type,
original carbon-14. That's exactly what you just said.
I don't think that's what I said. I think I said that the molecules themselves have more carbon in them.
You said they have a natural distribution depending on the tissue type.
Yeah, a natural distribution of carbon atoms in general.
Yes.
Yeah.
It's original.
So if you're
so
incorporating new carbon, then we would expect that new carbon to incorporate differentially based on the tissue type.
So backing up just a little bit in the way I actually organize this, there is also carbon-14 found in diamonds.
Yep.
There's also carbon-14 found in coal.
Sure.
So the
what
carbon.
do you think is the number one contaminant in diamonds? That's not.
Say again?
What do you think is the number one largest share of contaminants found in diamonds?
I don't think they're finding contaminants in diamonds.
They are. Even in gemstones, in fine quality cut gemstones, the number one contaminant is nitrogen. You're going to find mostly carbon atoms in a lattice, but you're going to find some nitrogen atoms interspersed with that. And how is carbon-14 created, I wonder? Oh, right, it's from nitrogen atoms. So it makes sense that we would find low trace amounts of carbon-14 in diamonds, which is what we find.
I think you completely bypassed one of the very common evolutionary arguments about this. Diamonds in particular are not always from atmospheric carbon-14. You can also have carbon-14 produced in the earth.
When diamonds are formed, they form with a small amount of nitrogen already inherent in them. Okay. It is the number one largest contaminant of diamonds.
So you're telling me, so it sounds like what you're telling me is that the AMS method for counting literally the atoms themselves, individual atoms, can't distinguish between a nitrogen and a carbon-14 atom?
Nitrogen decays into carbon-14 via neutron capture.
And you're telling me that the AMS method can't distinguish. Otherwise, you wouldn't get this false reading.
You get carbon-14 in carbon atoms that derives from the nitrogen that was already in the diamonds.
So you've already said it. Diamonds not being living tissue at all, and never were. Animals are. They also have nitrogen in them. If what you said was true, then you would also have contamination in living tissues, or once living tissues, as it were.
Yeah, it's a very, very small amount of carbon-14 that you find in diamonds. I mean, it's barely even a blip on the mass spec.
That is actually not true.
It is true. It's statistically barely different than a zero value.
So I went back and
error bars for.
I went back and looked, and to be perfectly clear here, these are independent laboratories that do this. And they typically do this sort of thing in the context of deep time, because most dating of this type has more to do with the evolutionary
Nobody is
idea of
dating
origins.
diamonds. They're not doing this in the
I know
context
that. I'm aware of that. But somebody was smart enough, and actually...
It was a creationist. It was Baumgartner or whatever.
Creationists were not the only ones who have actually tried to date or find carbon-14 in diamonds. That's a complete myth.
Baumgartner, I believe.
Independent secular scientists have done this as well.
And it doesn't... Have you ever done a mass spec?
No.
Well, if you do, then you'll see that you get signals and a whole lot of noise. You never, ever get a zero value in a mass spec. You get a ton of noise.
Never, ever?
Yeah, no, it's all noise, fluctuations at the bottom level. And you just have to look for the signal in the noise, and you can use algorithms to see where your signal is strongest whenever you run any kind of mass spec. So you're going to have a background noise for all of this. And the amount of C14 that are found in diamonds via mass spectroscopy, that's how they're doing these measurements, is within that background noise amount.
Actually, it's not.
It is.
You can get ages that range in the 45,000 down to about 34,000 from diamonds. And
everything I've seen was around 55,000, which is right at the very threshold of where you barely have any C14 in the sample.
Sorry, you need to look a little harder. They go all the way down to about 35,000. And to that point, 35,000 is well within, as a matter of fact, so is 40 and so is 45,000, is within the accepted range usage of carbon-14.
Yeah, that is.
And so you can easily fall below the 40,000 year mark with diamonds. Now, you made the comment that you've got all this noise and you have to kind of figure out where the energy spikes are to determine what the actual carbon-14 signature itself is, right? If that's true, and I'm not contesting that it is or isn't, I'll basically just say I agree with you. If it's true, you would be able to calibrate all the noise out of every sample you took.
Yeah.
Or if you couldn't, no carbon-14 dates would be valid for anything.
Yeah, that's why the amount that we find in diamonds is basically noise. It's not signal.
It's not noise.
The amount look, this is what I want to say. If you use an improper methodology, if you apply a method incorrectly, of course you're going to get incorrect results. If you have a mathematical equation and you don't use PEMDAS, the order of operations, you're going to get the wrong result. That doesn't mean that the equation that was wrong. That means that you didn't apply PEMDAS correctly. If you don't apply radiometric dating correctly, you're not going to get the correct results. If you try to radiocarbon date a non-living material like a diamond, you're obviously not going to get the correct results because you've incorrectly applied the methodology.
So let's be clear here. The labs that do this, they're independent labs that don't do creation science per se. If they don't know what they're doing and they're the ones that did the test, if they don't know what they're doing, then how can any of their dates be correct?
They're not radiocarbon dating these diamonds.
Yes, they are.
They are not. Even if they're measuring the amount of C14 in them, and they could be doing that. I'm not saying that there are no diamonds that could have C14 in them. I don't know. Like I said, I've seen the studies where it's a very small trace amount. 55,000 years was the date based on that amount. It's basically noise. If you're saying that there are studies out there where they are getting noticeable amount of C14, I haven't read them. But if you send them, I will read them. But I will guarantee if these were not creationists, they were not radiocarbon dating these diamonds, because you don't radiocarbon date anything that's not living material. You only radiocarbon date living material that was made by breathing organisms.
They don't. So let me put a real fine point on that. They don't carbon date coal or dinosaur soft tissue either, but they are living organisms. Dinosaur soft tissue, not bone, but they'll do the bone too if you pay them, because that's what they're there for. They're there to make money and earn a profit on their services. If you pay them, they will do it. They're living tissue. You still find the carbon-14. If the comment you made about the background noise had any validity at all, and I'll be honest with you, like I said, I'm not even disagreeing with that point. You would calibrate it out of everything, including the diamonds, and you still get more carbon than can possibly exist in 1 million years. It can possibly exist in 100,000 years, because you're up to the 1% roughly. You're up around the 1% of modern carbon at that point, and it's still there. But the whole point of the diamond study is because of all the things that you could do, diamonds are the least likely to be contaminated from outside sources because of how tight the lattice structure is. The most likely is living tissue because it's porous and it absorbs water.
Yeah, unless you have a source of C14 within the diamonds, which you do.
That's
Gentlemen,
what I'm trying to tell you. C14 decays way too rapidly to have any source left.
Yeah, N14 decays into C14 via neutron capture, and there is N14 within diamonds. So you have an internal source that can generate new C14 within a diamond.
Okay, TRock, take a note if you'd like to. If there's anything you'd prefer to respond to from Grayson there, we'll give Grayson the last word on that subject. Subject 4, radiocarbon dating. So you both, firstly, you both got an award for endurance because we're now at 2.5 hours of basically free-flowing discussion. So great job, technical, comprehensive, and definitely an engaging debate. So we're moving on now to subject number 5, which is the final subject of the night. Then we'll do 3-minute concluding statements, which basically is just to wrap up thoughts and points. And then we're going to get into some audience questions. So TRock, we'll hand it back to you. Topic number 5. Here we go.
Okay, we're talking about dinosaur soft tissue. So I'm going to skip past the intro with Mary Schweitzer and all that. There's some very interesting stuff. Grayson mentioned cross-linking, which, of course, there's nothing new about that. And most of the discussion you've probably heard before today has to do with the specific chemistry behind cross-linking. I'm not going to do that. I can easily demonstrate cross-linking the way Mary Schweitzer did by simply whipping out a piece of beef jerky and throwing it on the shelf. That's cross-linking. So what she did, I'll touch on this briefly because it's relevant to my next real point that I'm going to make. What she did was she took and centrifuged iron out of some ostrich blood, I believe. Would you agree with that?
I don't know about ostrich blood, but I'm aware of Mary Schweitzer's work.
Okay. This is where the cross-linking idea came from.
It's chemistry. I mean, I don't think Mary Schweitzer originated cross-linking.
I didn't say that. I said what I'm saying is the use of cross-linking to explain the preservation of dinosaur soft tissue.
When we look at the dinosaur soft tissue, what we see is the collagen is highly cross-linked. That's an objective fact.
So, to that point, what she did was she wanted some explanatory power. She found red blood cells, and there are specific quotes where she says red blood cells. And she said she did not believe it until they had done it 17 times. To me, that's unprecedented. Why would a scientist think they had to do something 17 times in a row to prove to themselves that what they were seeing is what they were seeing? Anyway, so the cross-linking thing, what she actually did was centrifuge some iron out of some ostrich blood. And she used that to soak the dinosaur soft tissue in. And for some period of time, hence creating her own version of cross-linking. And then what she did was after that part was done, she put it into water, set it on a shelf, and walked away for 2 years. And then that became the de facto explanation for the preservation of soft tissue per your own comment a few minutes ago. Okay, so here's where I want to go though. Forensics, real forensic science. And this is where Mary Schweitzer's approach was, I mean, I don't want to denigrate her in any way. She's obviously a very technical person, but she completely missed the mark on this one. And I'm going to explain why. There were, where do I have this? Make sure I get this.
Just so I can be clear really for a second, just to explain to the audience, because I saw some questions about what cross-linking is. Collagen is normally kind of like a trifold. It's kind of like DNA is like 2 lines twisting together. Collagen is like 3 lines twisting together, but those lines are not necessarily chemically bound together. They are physical interactions keeping them together. But cross-linking basically creates chemical bonds between different parts of the collagen fibers that makes them extremely stable. So they do not decay in the same way that non-cross-linked collagen decays. So it is new chemical bonds that are formed that stabilize the collagen.
Yes. Yes. Cross-linking is basically a change in configuration of the iron atoms in this case, because she's not trying to invoke.
Not the iron atoms.
She's not trying to. She
Iron
literally.
atoms can catalyze cross-linking, but they are
Okay.
not like.
But the point is, it's not an external iron source. It's not an external iron, non-biological iron source. She was going to specifically ostrich blood because of the evolutionary paradigm that birds evolved from dinosaurs, whatever. But that's why she used ostrich blood to have something comparable in her mind to the dinosaur soft tissue. Okay, and her point was that it was not to be explained by non-biological iron. Whether it's the catalyst or otherwise is kind of irrelevant. It's biological and it's related to.
Well, we have seen non-biological iron cause cross-linking in greenland.
She's weeding that out though, and what she's saying is, she's saying it's in situ to and native. It's endogenous to the animal itself that was preserved.
Well, that's not necessarily the case, but okay.
So she published this in the open literature that you do trust. So I'll just leave it at that. Anyway,
I mean, I agree with Mary Schweitzer's work. I think she's a good scientist,
and I think she's a good scientist too. Like I said, I don't want to denigrate her, but she missed the mark completely on this one. Where she should have made her starting point was not highly centrifuged and concentrated iron. She should have done her starting point with taphonomy. How did the animal die? That's where she should have started. Okay, so what I did was I went and looked at a forensics page that has nothing whatsoever to do with origins in general. This is just basic forensics. The following factors affect the progress of decomposition in water and can be easily altered by disposal method: clothing, perimortem trauma, access to the water surface, energy of water movement, biodiversity, floor substrate and geology, body weight, water and air temperature, moisture, pH, partial pressure of O2 and other gases, and the local chemical environment. Okay, when remains are exposed, and this is from this article, it was at newhaven.edu, when remains are exposed to aqueous environments for prolonged periods of time, the body experiences disarticulation and the detachment of soft tissue. This is forensics. This is what they do whenever they're trying to solve a crime, for example, a typically murder crime of some sort. That one statement is extremely important here, because how do you find most dinosaur fossils? You find them highly disarticulated. Okay. The average quantity of DNA that was detected for bone samples that were incubated in fresh water for 72 hours was approximately 0.0209 plus or minus 0.0231 nanograms per microliter. This was a significant loss of DNA at about 350-fold. That's fresh water. She did three different salinities, I'll say. One was fresh, one was a kind of a middle salinity, and the other one was a higher salinity. Okay, the average quantity of DNA that was detected for bone samples that were incubated in salt water, in other words, the higher salt concentration, for 72 hours, that's the key, 72 hours, was approximately 4.87 times 10 to the minus 4, plus or minus, in nanograms per microliter. In other words, about 15,270 fold. That's also important because most dinosaur fossils are found in a marine sediment environment. So much faster rate for saltwater than is for freshwater. And to be specific, she's talking about bone and bone soft tissue as opposed to other types of soft tissue like skin and stuff like that. Of the three aqueous environments, saltwater exhibited the greatest DNA loss. This was consistent in both the bone samples and the tissue samples. 72 hours, that's the key. Disarticulation. What this says about Mary Schweitzer's experiment is she was basically insinuating that blood pooling, for example, could create a high iron rich environment to, per your comment, catalyze the cross-linking.
Yeah.
The problem is that the way you find the bones, they've already been disarticulated through high levels of water degradation before they were deposited.
Okay, what about iron-rich soils? That's pretty common.
Like I said, she eliminated that as one of the contributors.
Well,
and the reason is because if it were an external non-biological source like what you're implying,
which we have seen evidence that it does.
It's the same problem. You would have had to have gotten it in there through water transport, and you would have permineralized the material instead of cross-linked it.
Nope. I mean, look, last year in Greenland, they found the oldest preserved DNA ever. It's like 2 million year old DNA. And you know why it was preserved so well for 2 million years, which is way farther than anyone expected to find DNA? Because the soil was very iron rich, and it was very dry, and it was very cold. It was in Greenland. You can look it up. It's horseshoe crab DNA from 2 million years ago in Greenland. The study came out last year. So we have lots of evidence that high iron in rich environments do cause cross-linking. The DNA was cross-linked.
Like I said, crabs, they live in the salt water that this forensic science is describing. They live in that salt water continuously. So at the instant they die, what you're implying is they basically became instantly fossilized, because if any days went by at all, crabs of all things get ripped apart in the bottom of the ocean very quickly. They can't sit there for a long time waiting for this fossilization. So the 72-hour thing that this forensic study shows, basically it invalidates the hypothesis put forward on this DNA, because it's too fast. It would have already been gone.
Yeah, I've got news for you. Fossils form from rapid, burial. Like all fossils form from rapid burial. So it's got to be rapid burial for you to have fossilization, or else it's just going to decay away. That's how every fossil's formed. That's
interesting, because that's what creationists say all the time.
That's also what geologists and paleontologists say, because it's
really
true.
Then how do you?
Every paleontologist will tell you that.
How do you get 3 meters of sediment, or 10 meters, or 20 meters? The depths are actually very thick. How do you get 3 meters of sediment and equate that to a long geological period if the sediments are all deposited really quick?
Yeah, because different layers are deposited at different rates. You can have some layers of sediment that are deposited very rapidly, and you can have some layers that are deposited very slowly, like limestone. So if you find uniformly laid down,
if you find soft tissue, or you find in particular DNA, and let's be a little more clear here, because to my knowledge, nobody's ever really found anything more than about 6 peptides or 6 base pairs long of DNA in ancient tissue, right?
We have lots of sequences from ancient DNA. That was going to be one of my main points in this, was that when we look biochemically at what we're actually seeing in these soft tissues of dinosaurs, we are not seeing any DNA. We don't find any DNA. We don't find anything that would decay quickly, right? We only find things that would be very stable, highly cross-linked collagens and other very stable molecules. In fact, are you familiar with Fuzz Rana? He's a creationist, and he has looked at this and said, this is evidence of the old Earth. This disproves a 6,000-year-old Earth, and he's a creationist.
He's not a biblical creationist.
He's a Christian, and he's an old Earth creationist. So I will say, with my point with this, we do find DNA in bones and in remains that are 6,000 years old. We do find DNA in them. We have never found DNA for dinosaurs. So
yes,
why don't
we have?
Huh?
We have.
We have not found dinosaurs.
You just don't read enough, apparently, because what I described, the 6 base pairs long, because DNA being a long, fragile chain of molecules, it's because of its length partially, and because of its fragility, a lot of it is hydrogen bonds, weak hydrogen bonds that hold some of the links together, right? Yeah. So there is a rate that you calculate, like a half-life that you don't like. But there's a half-life rate you do for that. Say, okay, the chain breaks after so much time, the chain breaks again, and you keep whittling it down. And it's just like the carbon-14 problem. You break it too many times. So what has been found in dinosaur soft tissue is up to about 6 base pairs long, which blows all real-time scientific study on half-life degradation completely out of the water.
That is not true at all.
Yes.
I don't know what creation.com article you got that from, but that
doesn't come from a creation article.
Now, here's something interesting. We actually have found DNA in dinosaur fossils. Guess what it was from? Bacteria, not dinosaurs.
So that's funny because actually, when you start reading these studies, first point I want to make is that if it was so normal to find even blood cells, we're not talking about DNA. If it was so normal to find this type of soft tissue and it just had this rather natural explanation to it, Mary Schweitzer and her team wouldn't have repeated the thing 17 times. Have you seen the video interview with Barbara Walters on that?
Mary Schweitzer did not find blood cells.
Did you?
She explicitly said she's not finding blood cells.
You are not reading her literature, apparently.
I'm getting this directly from Mary Schweitzer.
Go. At what point in history is my point? Go back and watch the video where Barbara Walters interviews her. She interviews her and she interviews Jack Horner.
Okay.
Look at the expression on their face. They are completely blown away by finding.
God, Barbara Walters was surprised?
No
way.
No, I'm talking about Mary Schweitzer and Jack Horner.
Okay, yeah,
they are completely.
I will acknowledge the fact that like Mary Schweitzer was going against the tide there. I mean, she's a great scientist. She stuck with her guns. She knew that her results were right, and she was proven correct in the end because people were not expecting these kinds of soft tissues. But what she did was that she treated these dinosaur fossils with chemicals that would erode away all of the minerals. And when the minerals were eroded away, there were still proteins and other soft tissues that were there, not red blood cells, to be very clear. There were like remnant structures just in the forms of like the proteins and like the different organic molecules there, but they were not red blood cells by any means or any stretch of the imagination. And she has clarified this when creationists have tried to say that. She has gone out, her paper now has a disclaimer against these creationist claims that she has put out because she's been taken out of context so often in this. But when you actually look what she has found, the actual chemical structures of these soft tissues, it is not at all, it completely debunks 6,000 years because it is not the kinds of structures that we would see after 6,000 years. It is significantly older than 6,000 years based on the actual biochemistry of what she found.
No, you're mixing worldviews to come to an erroneous conclusion there. I've got a couple quotes here from her directly. When you think about it, the laws of chemistry and biology, where did she get those laws? She's never been a creationist, a young earth creationist.
Yes, she has. She used to be a young earth creationist before she pursued her degree.
Okay. Well, this is her in this particular real field study when she is not a young earth creationist.
Well, listen to her story. She used to be a young earth creationist, and then she got an education, and then she actually became a scientist and contributed to the field, and she found these dinosaur soft tissues, and guess what? She's still not a creationist.
So listen to the quote. When you think about it, the laws of chemistry and biology and everything else that we know say that it should be gone. It should be degraded completely. And that was in Nova Science Now. That was her direct quote. The presence of original molecule components is not predicted for fossils older than 1 million years. And the discovery of collagen in this well-preserved dinosaur supports the use of actualistic conditions. And this is why I say she missed the mark. She says actualistic conditions here, but she should have started with the taphonomy, not the ostrich blood centrifuge. Actualistic conditions to formulate molecular degradation rates and models. If she started with taphonomy, she wouldn't have had enough to try and assign a half-life of degradation to, rather than relying on theoretical or experimental extrapolations derived from conditions that do not occur in nature. And I totally agree with her, because if she had started with taphonomy, similar to how forensic science does their work, she couldn't have, she would absolutely not expect the collagen or anything else to last that long. So she says,
here's the question then. Why is it that when we look at things that are actually accepted by the scientific consensus to be 6,000 years or 4,000 years or whatever you want to say the flood was, right? When we look at them, why don't they look like these dinosaur fossils? Why is it that you find all kinds of organic molecules in them that you can't find in dinosaurs, that like when things are actually 6,000 years, they look 6,000 years. When you look at these dinosaur fossils, they look different. They're not looking the same.
You're looking at two different things typically, and this is a real common evolutionist mistake. You're making a really big logical fallacy here, mainly because you've got some kind of factual fallacy in the background, I think. But it boils down to this: if you find something that has a more modern date assigned to it, it is almost given that it is not flood deposit. It's pretty much a given. It's not flood deposit. It was buried and fossilized under completely different conditions. So
I don't think you see how that's relevant, because you believe, right, that
why did you bring
after the flood, wait. You believe that after the flood, it was only a couple hundred years before the pyramids were built, right? It was very quickly after the flood, correct?
More than a couple hundred, but yeah, quickly.
Okay, so when we look at Egyptians from Old Kingdom Egypt, we do not see the same kind of biochemistry that we see in these dinosaur fossils. Like that, they are much more.
You know that
we still get DNA samples.
You do know they used chemical embalming on them, right?
Yeah, you do know that there were chemical treatments on these dinosaur samples that Mary Schweitzer used to get these results, right?
She removed the mineral. That's not the same as what they did to the Egyptians.
Then let's move on past the Egyptians. Let's look at societies that didn't use mummies. You can use any. Look at Vinca Man. Okay, he's like purported to be about 5,000 years, or no, more than 5,000 years old, 6,000 years old. So this would be right around that time, and yet it's the same as the Egyptians. We see the same kind of chemicals, like biochemicals.
They wouldn't be the same as the Egyptians, because they use specific preservation chemicals. And you're telling me that this other case they did not. They wouldn't have the same chemical signature.
Yeah, well, they do. They definitely don't have the same chemical signature as these dinosaur fossils, which proves that they are not the same age.
Tell me, no, it does not. That's a major logical fallacy. How was that particular fossil find? How was it fossilized? What process was involved?
Yeah, it's not fossilized. He's not permineralized. Notice, no human fossils are permineralized because there's not enough time.
Yes, there is.
No.
Most of the human fossils you're finding that aren't permineralized, if indeed that is the case, I'm not disputing that.
They're all still bone.
If they're still original bone, the majority of them, for instance, like the Neanderthals, are buried in caves, and they're buried in the dirt in a dry environment. Mm-hmm. So no, you're not going to get a ton of permineralization in a dry environment. You get permineralization from water transport.
Okay. Well, we can look at all kinds of different human remains, and none of them are permineralized, but all of the dinosaur ones are. You don't find any dinosaurs that still have, like, not permineralized, right?
That is completely not true.
It is.
No, you can. As a matter of fact, there's a place in Canada where hadrosaur bones were found on top of the ground, unpermineralized, and they were ignored for a very long time because the locals thought they were just cow bones that had died, whenever in the past.
And they were still mineralized.
No, they weren't.
Yes, they were.
And so this brings up one other really interesting point about the whole Mary Schweitzer, Jack Horner thing. Mary had gone to Jack and said, "Look, this is what I found." And she said something to the effect of, "It stinks out there." And I think she was referring to Hell Creek, Montana. And you know what Jack Horner said to her? He said, "Yeah, it's well known. All of those dig sites like that stink. Why do they stink? It's because there is soft tissue in those bones, and those soft tissue has been found by now, as you well know."
No, that's ridiculous. Go smell a dinosaur bone. It's not going to smell.
That's not what Jack Horner said.
Gentlemen, excellent discussion. You know what? Let's wrap it up here. We are 2 hours and 45 minutes into this. We got through each point, though. I wasn't sure at first when we had basically an entire debate on Earth's magnetic field. You both did great endurance, and so I'm happy to say we got through all 5 points. So, okay, we're going to move into if you'd like to, gentlemen, 3 minutes just to wrap up your thoughts and points, as you both might feel there's a few things hanging. And so take the 3 minutes, use them however you'd like to. And then we are going to get into about 25 minutes worth of audience questions. So TRock, go ahead, take 3 minutes to wrap up your thoughts and points.
I guess I won't spend a whole lot of time going back over any of the technical information, just because we've been pretty exhaustive in our conversation. You can go down a lot of rabbit trails like that. So I'll just summarize real quickly. When you do modern scientific endeavors that affect real-time things, and you apply those same methods to investigating the world in the past, you come up with some bizarre conundrums that should not exist if deep time were true, is the gist of this entire presentation. Use real-time science that you would use, like I was describing, forensics, as it's used in criminal investigation, and use those methods in your investigation of things like dinosaur soft tissue. And dinosaur soft tissue, honestly, is not the oldest soft tissue by a long stretch. We don't have any time to go back into that, but it's not. But anyway, use those methods that you use in modern scientific techniques that have nothing to do with origins and apply them to the past, and you come up with some bizarre conundrums. We see that in the physics. And so the solutions always seem to be some imaginary conditions that existed in the past that make modern methods invalid in that particular setting. So I'll just recap real quick. Earth's magnetism puts about a 10,000 year limit on the age of the Earth, because the reversals that do cause the spikes that were described actually accelerate the overall energy decline in the field. So 10,000 years basically puts a cap, because the half-life is so short in the 200 years worth of data that we have. Erosional rates at very modest modern day average rates, when you extrapolate that into the past, you find out that you really shouldn't have continents anymore. So when you combine that with lunar recession, and you find out that in time, over time going backwards, the moon comes closer and closer to the Earth, the gravitational influence is increased by the inverse square law, but the kinetic energy of the tidal wave is also increased by at least that much, actually more. You find out that erosion rates, the further you go back in time, the bigger the problem they are. So today's rates are actually not sufficient to describe what happened in the past, but yet they still limit the age of the Earth to about 10,000 years. Okay, or 10 million, sorry, at an absolute max. Radiometric decay, we talked about carbon-14. Super short half-life. You have to imagine this internal source that was talked about, because they normally would default to an idea of neutron bombardment from an external radiation source like uranium or something like that. But the problem is that rate of rebuilding carbon-14 is about 13,000 times too slow if it's absolutely perfectly accurate every time a neutron flies into a nitrogen atom. Okay, dinosaur soft tissue also has the same carbon-14 in it. So if diamonds can be contaminated in any way, so much more so for any living or once living tissue, because it is all porous and absorbs water and external elements from the environment rather easily, where carbon-14 does not. And so carbon-14 limits the age of the Earth to no more than 50 to 100,000 years. Dinosaur soft tissue, I said 20,000 earlier. I still stick by that, because when you do a proper forensics investigation, you find out that they were highly degraded and disarticulated before their time of burial, which means there is a tiny minuscule fraction of soft tissue or anything else left, carbon-14 included, left to deal with, to explain. That's what you're actually trying to explain. How much should have been left at the time of death, not how much theoretical the once living animal had, but how much was left after it was at the time it was buried. And so that limits very well below the standard rates given for collagen duration, other types of protein duration, well below those numbers that are typically in the 600,000 to 1 million year range. And that's how I get it down to more realistically less than 20,000 years. So with that, I yield my time. Thank you.
Thank you very much there, TRock. Grayson, would you like a few minutes to wrap anything up as well?
Yeah. So I think went pretty well as certain terms of showing the faulty reasoning, the mistakes in TRock's reasoning about each of these 5 points, explaining why, for example, Earth's magnetic field has variations in strength over time. So there's no limiting time there, showing that erosion rates are compensated by plate tectonics. I've seen people in the chat asking about what the soil accumulation on the ocean floor that's done away with by subduction. So plate tectonics accounts for all of these erosion processes. It counterbalances them. And the rates of erosion have varied throughout geological time as well. The moon being closer would cause more tidal activity, but it was closer way before any life was on Earth. So that wasn't a problem for life. I mean, this is like microbial life, which is not really impacted by that kind of thing. And then the increased erosion is again counterbalanced by plate tectonics. The amount of new material being generated and the amount of material being destroyed by erosion has varied throughout time, but they roughly counterbalance each other out. Although I think now we're at a higher erosion rate than is typical in the past. And then carbon-14, obviously, I went through a number of different processes like recrystallization or bacterial ingrowth or just being close to radioactive materials. That is going to generate new carbon-14 in these samples. It is not the original carbon-14 that he's talking about, so that addresses that. And then with the dinosaur soft tissues, that was really fun because obviously the biochemistry in bones in 6,000 years is not the same as the biochemistry we find in these dinosaur soft tissues. They are very chemically distinct, thus proving that the dinosaur bones are not 6,000 years. It is literally proof against the creation model, these dinosaur soft tissues. When you actually analyze them from a biochemical perspective about what these soft tissues actually look like, we can see that they don't look anything like 6,000 year old soft tissues should look like. So I think I've done an adequate job of debunking each of his points, showing where the faulty reasoning is, and providing a scientifically accurate explanation for these supposed problems that TRock has brought up for an old Earth. So old Earth wins, Yak loses. Check out my channel if you like this kind of content. Plan on continuing to do debates like this because I find them very fun, and I would like to spread out too and do debates on topics more than just like young Earth creationism. Like to maybe do a flat Earth debate. If there's any flat Earthers out there, hit me up. I'd like to do debates on like race realism or I'm open to debating politics too. So I'm really open to any kind of debates. I've got a debate coming up. Donnie, I don't know if I think the date's changed, but I've got a debate coming up with Nephilim Free on this channel, so stay tuned for that. And then I've got a debate coming up on Modern Day Debates on Big Bang cosmology. So a lot of things, exciting things coming up down the pipeline, and I will be continuing to put out videos on my channel as well. So go ahead and check it out down in the description. As based theory, as in the opposite of cringe theory, like creationism.